how do you do that on a Mac? Oh.
Wait, alright. Press it.
Again, this go here. Yeah, cool. Cheers. Hey guys, thanks for joining. Yeah, we'll get started 5 past. So 12:05. Yeah, there's the. Where is it? I had it somewhere. I was just using it. It's here. I mean, do you guys need the microphone or you could? Okay, cool. I can't move to something.
Oh, there you go. Okay. This is pairing.
Oh, okay. Oh, that's so it's blinking. It's pairing. Okay. Hey guys. Hello. Thanks for coming. That's set up. And the stream delay is on? Yeah, okay. Cool. All right, I think we'll get started. It's about 5 past. Let me just check the audio is working again. Yeah, okay. Welcome to the crash course for. Sorry, we don't call it a crash course anymore. We'll call it a revision session for your final exam. So just a bit of an introduction for those who don't know me. My name is Hassan. I'm a demonstrator for this course. I'm in my final year as well, so this will be the last revision session I run for this one. But I did run this one last year as well. So if you're looking for extra additional resources, I believe in that one, I just went through all the past papers. I picked the hardest questions and I went through them. So I think it was like 2020, 2018, and 2012 or something. So if you're definitely looking for additional resources, I would highly recommend you watch that stream as well. But just for a bit of an overview as to what's happening in this session. So the main thing I really want to cover is how to prepare for your final exam. And if you're going to take away anything from this session, what you really should take away is the first 20 to 30 minutes. Then I'm going to go through a few topics which are a common point of difficulty. So power amplifiers and setup and hold time. I'm going to go through those and explain them just in a bit of an intuitive way. So not necessarily going hard into the maths there. And then I'm going to go through past paper questions for the next 2 hours after that. And I believe the past paper questions I picked were from the last most recent paper. Cool. So how to prepare for the final exam. So it's the main thing you should hopefully take away from this course is, the main thing you should hopefully take away from this course is that it's testing your understanding. It's not testing your how much you can remember, how much you can memorize. Content in the lectures is really important, but what's more important is how you apply those topics in the lectures to different contexts. That's what you're going to be tested in the exam. And if you've had a look through the past papers already, hopefully you've got an idea of that, that Torsten doesn't reuse questions. He makes unique questions every single year, which means if you're trying to rote learn the content, you're going to find it very hard to in the actual exam when you have to come up with your own unique solutions. So just a bit of a summary of what I just said. So unique questions every year. Rote learning does not work. If you try rote learning, you're going to find it very difficult come exam time. And something also that's really important is there's not necessarily any correlation between the number of past paper questions you do and there's not necessarily a correlation between the number of past papers you do and the mark you get. I think Torsten releases like all the way up to 2012, I believe is correct. So a crazy number of past papers. But that doesn't translate to higher marks. The average mark for this course is probably somewhere like 60 to 70. And so if more past papers resulted in more marks, the average mark would be like 95 for this course. So the key takeaway from that is it's really quality over quantity. Really spending time with each past paper and taking out from it as much as you can, rather than just trying to blitz through as many as you can. I've seen students who do just five past papers or just 3 past papers, but spend good quality time on those papers, do a lot better than students who just do like 30 past papers. Okay, and really focusing on understanding content and building intuition. So the way I always like to study for my own courses, and also when I'm teaching other students, is I always think, could I explain this topic to someone else? If someone asked me unprompted, hey, how does this work? Or how does this circuit work? Without looking at my own notes, could I give an intuitive explanation to someone? So writing notes is good for the content, but often writing notes gives us false hope. It gives us a false sense that we understand the content, when in reality, we really don't. So whenever you go past the topic, so before you actually go through the past papers, the first thing you should do is make a summary of all your notes, which is always really good. But don't just write the notes. Ask yourself, can I explain this? If not, try and explain it to yourself. Okay, try and build an intuitive understanding. And if you've been my student and you've seen my explanations to certain things, the only reason I'm able to explain it so well to you guys is because that's how I explained it to myself, to understand the topic. So that's really important. Okay, and so what are the golden rules of past papers fundamentally? So the first golden rule is do not look at the solutions when you get stuck. This is really, really important. It gives us a false sense of hope when we look at the solutions, because often the difficulty in the questions is not getting from, it's not the final solution of the question. The difficulty in the question is thinking to yourself, is the question really simple? Is it really complicated? And it often feels like there's a million different pathways you could go for a question, or sometimes you can't see a pathway at all. As soon as someone sort of nudges you in the right direction, then it becomes really obvious and you almost think to yourself, oh, I could have thought of that in an exam. But again, there's that false sense of confidence because the difficulty is coming up with that initial direction yourself. And so if you just skip to the solutions, you're going to get very uncomfortable in the actual exam because you're going to be itching for a solution to sort of nudge you in the right direction. And then golden rule number 2, do not look at the solutions when you get stuck. Golden rule number 3, do not look at the solutions when you get stuck. Any guess what the 4th golden rule is? But in rainbow. So I just really need to emphasize the importance of this. You really have to get comfortable building your own intuition for questions. It's really, really important. It's uncomfortable. It sucks at first, and you're going to struggle for the first 1 or 2 past papers, but it does get better if you allow yourself the room to learn and build that intuition. So again, just summarizing. So difficulty in the questions has gone from A to B, not from B to C. So once someone gives you how to go to A to B, it's pretty obvious how to finish up the question, how to get to a solution. And again, just get comfortable not having access to those solutions. And yeah, so it's really challenging at first, but this is a very unique course compared to other courses. Other courses you may have been able to get away with rote learning. This course really does punish you if you try to memorize. And so even if you have a great understanding of all the content, but you don't know how to apply it to new situations, you'll find yourself in a lot of trouble when the exam time comes. So, and again, just emphasizing, it's really hard at first. No one comes built or born with intuition. I know myself when I was doing these past papers, I struggled quite a lot. And the only reason I'm so good now is because I went through this process of struggling. So if you're going to struggle at first, it's normal, but just please don't look at the solutions. Practically begging you at this point. Don't look at the solutions. Try to come up with your own direction. So how to make the most of past papers. So the first thing you should do is attempt the past paper under strict time conditions. The importance of that is twofold. So the first reason being, the exam is obviously under time conditions. You need to get used to being under a high pressure environment and being able to think quickly on your feet. And also it gives you a good gauge of where you're currently at. So it gives you an understanding of here's where I'm at, here's how much I was able to do in these 2 hours that I've set for this paper. Now for the first paper or first few papers you do, you're not going to be able to answer almost any questions, right? You might be able to answer a few questions here and there, but you're going to find it really difficult, which is completely normal. So you ask yourself, am I confident with my answers? Often it's no. So what you'll see me do in the lecture, when I go through the questions, is you revise all of the content in the question. So you go, not just the question itself, but the context of the question. If there's a linear dropout regulator, you ask yourself, can I explain how that linear dropout regulator works? And once you start building, deconstructing the questions into building blocks that you do understand, it gets easier to put them together. Then, and this is not under time conditions. So once you've done your time condition, timed 2 hours, you revise, you reattempt the questions, and then you just keep going in this loop until you are confident with your answers. I mean, again, no solutions yet until we're somewhat confident with our answers. Now, you're never going to be fully confident, but as long as you've put something down, it's really just put an answer down and then try and check your answers and just do it very slowly. Don't skip to the solutions and just scroll through them. Go through them one by one very methodically, okay? And just to, I guess, emphasize what I meant by that, you have a question like this, which is extremely overwhelming. I mean, I'm 2 years out of the course and I see a question like this and I still initially get quite overwhelmed. But then what you can do is you can just break it down into the things that you do understand. So first thing I see is there's a battery discharge curve. So you might want to ask yourself, well, what does a battery curve look like? I see an LDO there. Can I explain how an LDO works? There's a transmission line there as well. So how does a transmission line work? And there's also a new thing, which is an LVDS driver. How does that driver actually work? And this is questions I'd be asking myself before I actually get to this part here. So this is really important here at the part where if you're stuck, what I mean by revised content in question is go over this content here and really make sure you're comfortable and familiar with all of the individual building blocks before you try putting them together for the question. And yeah, was there any questions on any of this so far as to advice or questions you might have for how to prepare for the exam? Cool. Actually, I think that's the last slide I have. But yeah, just the general, yeah. Yep. Mm-hmm. Yep. That's a good question. So I think, so the first thing I'll say is the notes you bring into the exam, you probably won't look at once. I saw someone bring in the Sedgwick and Smith textbook, and if you've seen it, it's like that hefty. So generally, I think where I think the usefulness in that paper is maybe in things you'll forget. Don't put things which you'll remember, like if it's a non-inverting amplifier formula, we should remember that. But generally, it's a really good opportunity to summarize your notes. And in summarizing your notes, so you're taking the long notes you've written throughout the term and condensing them into a few pages, it's a really good way of studying the content again. So it's hard to say if there's one strict rule as to what you should bring into the exam, but things you think you'll forget is what I recommend. Definitely put formulas. So I think there's some formulas in week 10 regarding probability distributions. I can't remember if they're provided in the exam. From memory, they're not. So definitely write those things down. And just generally things you might forget. If you go through the past papers and there's something you see there that you think you might forget, or a topic or content, feel free to put that as well. But generally, I think it's a really good study resource. Yeah. Yes. Yep. Yeah. Mhm. Yeah, good question. I just realized people online probably can't hear what I'm saying. So the question was about the suggested solutions and how that often Thorsten reminds us that they are just suggested solutions, and there's often multiple possible solutions to an answer. And then so is the point of developing intuition to know if your solution is also a good solution, even though it's not written on the formal solutions by Thorsten. Was that? Yeah. So good question. So I think, yes. So definitely, I think the point of building up that intuition is to know, is the solution I've written feasible? Because the solutions, so there are some questions where there is only one solution. So if it's like, calculate what this resistance should be, and it's very obvious that there's only one way to go. But often some questions are written as like estimate or approximate, and you have to give approximations. What I'll say is that when Thorsten's marking the papers, he's not, maybe lenient isn't the right word, but he's, when it's an estimation question, he is very aware that it's very broad. So even if you're maybe if you don't have the best possible approximation or the best possible for justification, he's a lot more lenient in marking those sorts of questions because he understands there is numerous multiple solutions that have different answers. And so definitely the point, I think, to build on to that question, when it's a design question, for instance, or a very open-ended question, sorry, definitely think, is there another solution? So I actually go through some examples of that in these questions, but ask yourself, would this solution work, or is there another possible solution? Yeah, so does that answer your question roughly? Okay, cool. Any other questions? Cool. I think if that's all, we'll just get straight into the actual content. Actually, so we just need to resize the ratio. Yep. Oh, yeah, good notes. And then let me just copy notes. I think that's all good. Okay, cool. All right, cool. And yeah, and just to finish up on everything I was saying, like this is a very, very hard course. So if you're struggling, everyone is probably struggling as well. I struggled quite a lot when I was doing the course, and it's probably the hardest exam you'll sit in a very long time. Probably, if you don't take microelectronics, probably the hardest exam you'll sit. Although in saying that, microelectronics is a very fun course, would recommend. If anything, that course is actually a little easier to digest because you've been through the sort of surprise of electronics taught by Thorsten. So yeah, it's easier to digest. So as mentioned, the first thing I wanted to cover was power amplifiers. So now what I intend to go through with power amplifiers is I want to talk about the different classes of operation because that's fundamentally what the power amplifier is about. So generally any power amplifier is it's a very simple circuit. So it's just a transistor. So it could be NMOS or PNP or NPN, so BJT or CMOS. I'm just going to draw a MOSFET because it's easy to draw. And generally it works, you have some sort of input at the gate, and then you have a load resistance. And often actually at this point here, you have a capacitor, and that's just to block any DC. Because if this is powering some sort of audio signal, then that DC will just blow someone's ears up. So yeah, and so that's fundamentally a power amplifier. The role of a power amplifier is simply to seems obvious, but just to increase the power of the input. And the way it does that is effectively by just flicking this NMOS off and on. So it's controlling, the input signal is controlling how much power we're drawing from the power supply at any given moment. So the amount of power we're drawing from here, so IL. Now, often this input signal is, so it's some sort of oscillating signal. And so what you can see is that when the signal oscillates high, it's going to turn this NMOS on and draw current from the power supply to the load. When the signal is low, it's going to turn the NMOS off. Okay, so it either pulls it to ground or to VDD, effectively giving us a swing of across the amplifier. And then the power at the amplifier is just V RMS squared. So sorry, V load RMS on R squared. No, so V squared on R. Just the standard power relation, V squared on R. Okay, so then there's a question of how do we actually operate this as a power amplifier in terms of the different classes of operation. I always like to think of it, and I gave the exact same analogy last year, was I like to think of it in terms of a tap and running water. So if I just draw for now, so let me just move this. What I'm going to draw is, so the gate voltage of the MOSFET, so the input voltage, as a function of current. So as a function of current that runs through the MOSFET. Now, the MOSFET has a particular threshold voltage that is required at the gate before it actually turns on. Now, roughly that, it's usually like 0.7 or something, can differ. The specific value doesn't matter. All that matters now is that there's some specific threshold. And up to this threshold point, the MOSFET won't turn on, but it will turn on. So once it turns on, then it's sort of kind of linear, and then it eventually saturates, right? So this is what we call the saturation point. Okay? So just at a high enough DC signal at the gate of the MOSFET, we turn it on, and then current can flow through the FET, and then eventually it saturates. Now, what dictates the, so let me just remove this for now. Just give myself some space. So what dictates the class of operation of the amplifier is specifically where on this curve we start the amplifier. So where is our steady state for the amplifier? That is the class of operation. So as an example, if I bias my signal at the input so that it, before even actually applying an AC signal, it has some default DC signal. So what this input signal looks like, if I just draw it. So I'm biasing it by default with an offset. So some VDC. So using the tap analogy, this would be if I turn the tap to halfway and it's just running. So it's just running on. And then what we do is we apply an oscillating signal around it. So again, back to the tap analogy, this would be, so if I've turned it halfway, water is running. And then this would be me like flicking the tap forward and back. So it's more water, less water. In this case, it would be slightly more current, slightly less current. So if I look at this graph, effectively what I'm doing is I'm swinging this way, swinging that way, swinging this way, swinging that way, just swinging around this operating point that we've chosen. And that is effectively class A operation. That's class A. And does anyone know what the problem with class A is? Just looking at it. What's the problem with a class A amplifier? Yep, so, but what if I didn't operate it that far? So I don't swing too far. So there are large voltage swings, but let's say I don't saturate it. Yep. Yes. So with the tap analogy, I've effectively just left the water running, and the water is always running. So I'm effectively just going from slightly more to slightly less, but current is always flowing. This FET is always on. So it's very inefficient. But what is it? What's a good property of class A amplifiers? What does it have going for it? Yep. Yes, linearity. It's very, very linear because you can see that the amplifier is always in an on state. So it means it's never being turned off. As opposed to class B, which sits right at the threshold point. So this means I'm biasing the signal with just enough to just get up to the threshold point, not any further. And then I'm here, and then I'm swinging back and forth around this operating point. Now, what we can see is the problem here is I'm going from on to off, from on to off. So would this be more or less linear than class A, this sort of operation? Less linear, because I'm starting at a state that is off and I'm flicking between on and off. That is highly nonlinear. But it's very efficient because we're only on for half of the time of operation, whereas as opposed to class A. And then class AB, so class AB sits in between here. So class AB. So class AB is effectively sort of a compromise between the two, and you effectively just pick where you want to be between class B and class A depending on what efficiency you want and how much linearity you want. It's really a trade-off depending on the specific parameters you're trying to meet. And again, using the tap analogy, which I really like, class B would be like if there's a lot of friction on the tap and you have to turn it quite a while before water will actually run, and we're sitting at that point there. Now, class C sits here, somewhere there. That would be class C. So you can see we're getting more and more this way. So we're going more and more by default into the off state. Just zoom out a little. Yep, so we're more, by default, we're quite off, but we're getting better efficiency, just more non-linearities. And then class D is, does anyone know what class D is on this curve? Where are we biasing by default for class D? Yes. Yep, but where would it sit? What, like, do I need to bias it with any input signal? Any DC signal? For class D, we don't. So class D actually sits right here, all the way at the start. So class D is the most extreme case of a switch. So in class D, we don't put in a sine wave anymore. We put in a square wave because we're literally flicking it all the way on, all the way off. So class D is often associated with a square wave input because we're going from on to off, on to off, on to off. Now, class D, I think, is the most, I'm not an audio person, but I think it's the most common in audio applications, like mixes and stuff like that. If anyone knows why, feel free to let me know. I think it's an efficiency thing, but I believe there's another application. Anyway, is there any questions on the different classes of operation here? So this is fundamentally when you're building your own power amplifier, really the first thing you need to consider. What class of amplifier do I want to be in? And now there's a small caveat with this, that the amplifier I drew on the top left doesn't actually work for class B. Does anyone know why? So the method of operation is roughly like the explanation I gave here applies to all amplifiers, but class B swings low. So class B, so if you look at class A, for instance, it's always positive. It never goes below to the negative axis. Class B, however, goes negative. So if I look at the amplifier here, what happens if I apply a positive signal here? What if it swings up? I turn the transistor on. What happens in a negative when the input is negative? So just for some context, if I have a negative input, let's say I'm alternating current, I also expect the output to reverse its polarity. That's how it should operate. If I have a reverse polarity at the input, the output should also reverse polarity. But if this is negative, what happens to the NMOS? So high voltage at the NMOS turns it on. Yeah, but in this case, nothing happens because NMOS is just singular. So NMOS just turns on for high signals, but for a low signal, the NMOS is just off. So it doesn't alternate the direction of current at the output because it's not contributing anything in the negative portion. So what we do instead is we use sort of a totem pole configuration with PMOS and NMOS. So one of them controls the positive part of the signal and one of them controls the negative part of the signal. So let me draw that. So often what we have is something that looks like this. So NMOS. And we send the input signal to both of these. Let me take our output there. Now, I'm just emitting things like the load and all that. That's there. And this signal is always comprised of VDC plus VAC. So the DC biases it into the operation, into the region we want, and then the AC signal just fluctuates it around that signal. And the amount you can fluctuate this AC signal, I'm only mentioning this because I saw it in a past paper. The amount you fluctuate this AC signal, or you're allowed to, depends on the transistors and when they turn off and on. So transistors have strict conditions for which they stay on. So the first being that the threshold voltage must be greater than the threshold voltage. But then there's the other condition about the drain source voltage being greater than the gate source voltage or the effective voltage. So you'll see that in a past paper. I don't want to go into too much detail here, but effectively, you can't just swing this infinitely. At one point, you swing it too high, and the transistors go out of their correct range, which for a MOSFET is saturation. Yeah. So now let's analyze what happens in this case. So if the signal is positive, what happens? So if the signal is positive, the NMOS turns on, and I pull signal from VDD to the output, right? So if this is, say, a high signal, so let's say, so I'll just draw what class AV looks like. Oh, sorry, class B looks like. So the gate signal, we bias it with just a bit of gate signal. So a lot less than before. And it swings more in this direction, but it swings a bit this like that. So I bias it just to the point where for a certain, let me just move that over. Okay, yeah, so I bias it so just for a brief period of time it's off. And that was, remember, for the efficiency. So in this case, when the signal is high, so in this region here, this NMOS is on, and that means we're pulling here this way. In the case where it's negative, the PMOS turns on, and we go this way. You'll notice we have standard AC operation. So when the signal is high, it's pulling from VDD, and current is flowing in this direction. But then in the case where the input is low, we are reversing polarity and pulling to ground. That's why we use this sort of totem pole configuration for our power amplifiers. Class A will work just fine with just that operation, that configuration there. But anything that is briefly off for any period of time needs both PMOS and NMOS, or for BJTs, PNP and NPN. For this one here, yep, this one. Good question. So let me see if I understand, just to repeat for everyone online. So the question is, in this case, we're pulling to ground as well. So what's the point? Yep. But in this case, so it's a good question. So the amount of power delivered to the load is dependent on the RMS value, right? So it depends on the amount we swing in the positive direction and the amount we swing in the negative direction, right? Because that determines the average value. So if we look at this case, for instance, so the main difference here is the direction of current, right? In one direction, we're only swinging in one direction. So we have a really high maximum voltage. Whereas in this case, we're biasing it with, so if this is, say, class, let's say this is class AB, then we are swinging in this direction in one case, but in this case, we're swinging in this direction. Because in this case, we weren't, like if the signal is high, sorry, that was bad. Let me try explaining again. So if the signal is high, so in this case, it's high, right? But the main thing to keep in mind is we're never really turning this amplifier off. That's the main point, right? Whereas in this case, we're turning one amplifier off and the other on. That sort of makes sense? This part's a bit hard to explain without the math, because truly what you actually put here is you put an AB an AB multiplier to bias the gate with a particular voltage. And then when you run through the math, you see that the swing voltage is a lot larger when you bias it in this configuration. But just at a high level, it's purely just because in this case, we're always amplifying a positive signal. So we're always above the threshold voltage, which means this amplifier is effectively always, it's swinging from more on to less on, more on to less on, which means we always have positive voltage, whereas in this case, we have both positive and negative swing, giving us more power. Yes, yes. Yeah, exactly. But yeah, I definitely do recommend going to the maths because it does explicitly show what that means. Any other questions on that question? All good? Okay. So the other thing that's really important to mention is we don't bias the amplifiers like this in reality. So I've been mentioning we just apply a DC signal. Why is this a bad idea? Why is it a bad idea to do this? So why might it be a bad idea to apply a DC signal? So I mentioned we're applying a DC signal. So let's imagine this is just a power supply. Why is this a bad idea? I think in the lectures this was a BJT, just so maybe it's more clear. So if you try doing this and you put it on your breadboard, you'll notice smoke coming out of your breadboard, especially if this is a power BJT. Why might this be a bad idea? So let's try and think about what happens in an actual power amplifier. So in the power amplifier, so you're going to have some sort of load here, some load RL. Now, as you turn on the amplifier, the power is going to increase, which increases what? As you increase power? So increases current. So sorry, current increases, which increases power, which increases what? Heat, so temperature. So heat increases, so that means, so the amount of, let me just draw it. So the amount of current through here increases. So that increases. That means the power goes up, and that means the BJT temperature goes up. And so what's the problem with this? So the BJT temperature goes up, then what happens? Yeah. So what controls the amount of current through the BJT is effectively this this voltage here. So the amount we're applying to this voltage here. So to turn it on, we need about 0.7 volts. But that voltage is now fixed at 0.7 volts, or whatever DC voltage we've applied. Maybe it's 2 volts, because we've got a constant fixed power supply source. And so what happens from here? Does the BJT calm down? What happens? So power increases, the BJT power, heat increases. And so in turn, what does this then increase? So if heat increases, the amount of internal resistance, so the internal resistance remains the same. So the more heat, the more power dissipated. The more power dissipated, the more current we need to achieve the same power level. And then we're kind of just going in a circle. And we achieve what's called, I think Thorson calls it thermal runaway. So eventually the power increases, so I'll just write it. So thermal runaway. This is effectively where we lose control of the amplifier, because power is increasing, which is increasing the heat dissipation, which is increasing the amount of current through the amplifier, and then which increases the power, which increases the heat, and we just keep going till the BJT blows up. Okay? What's a better way of biasing this amplifier instead of using a constant fixed power supply source? So a better way, and it'll make more sense maybe with some context, is to use to usually use something like a Zener diode, right? To use something like a Zener diode. Does anyone know why a Zener diode might be better? So a BJT kind of has self-regulating mechanisms. So a BJT intrinsically, so this may be a bit of physics, but when the BJT is increasing, the heat is increasing, it will regulate, it will decrease this voltage when it senses that an increase in current is needed, to sort of balance out the increase in current that's needed versus the gate voltage that lies here. And sort of, in a sense, regulating its own voltage. Whereas in the previous case, what we had was a fixed power supply. So in this case, because we're fixing the gate voltage, we're not allowing the BJT to self-regulate. So in the case of when this increases by, say, 1 degree Celsius, what happens is that the BJT thermally links with the diode because they have similar thermal coupling profiles, which means that when the BJT increases by 1 degree, the Zener diode also increases by 1 degree. So they thermally linked on our breadboard or PCB. That means whatever happens at the BJT happens at the diode. Then can we picture what happens next? So let's imagine there's an increase in power with the Zener diode configuration. So the Zener diode is effectively clamping the voltage at some particular voltage. But the amount it's clamping also changes. I think it's 1 millivolt per Kelvin or something. But so that effectively changes the gate voltage at the base of the BJT. So what might happen next? Yep. So exactly. So if there's an increase in heat here, so I should mention that this is actually, so if this changes by 1 degree, it's minus 1 millivolts per Kelvin. That's probably a wrong number, but the voltage decreases by about 1 millivolt per Kelvin. So if the heat increases, that then decreases the gate voltage, so reducing the amount of current that flows when the power is increasing. So thereby regulating. Whereas when I had this DC supply on the side, it was fixing the gate voltage, not allowing it to self-regulate. So if we have this diode in place that thermally links with the BJT, then we don't have this issue anymore because it self-regulates the gate voltage when the power increases. So dropping the amount of voltage at the gate. Does that kind of make sense? This is quite a tricky concept, but really important if you're building your own power amplifier. To make sure you bias it either with this or you use something like a VBE multiplier. But in that case, the same thing is happening. The resistors in the VBE multiplier are thermally linking with the BJT. So if the resistor voltage changes, the BJT voltage also changes. Okay. Mm-hmm. Was that a power BJT? Because you have to be consuming quite a lot of power to notice this problem. Yeah, like if you're not operating it as an actual power amplifier, then yeah, you don't really notice this as a problem. Yeah. Yeah. Do you remember what the current was there? Was it like? Yep. 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 So these power BJTs are usually rated up to 1 amp, and they can easily go up to like really, really high wattage. So yeah, so I think you might notice a tiny bit of thermal runaway, but it's happening at such a small speed that it's not noticeable for consumer electronics. Cool. Was there any questions on this? So quite a lot to take in for power amplifiers, but generally the main thing to take away is just the different classes of operation. In terms of what you see here, one other thing you might see in a past paper that I've seen is often the power amplifier. So again, just assuming class A operation. So this is VAC. So instead of biasing with a DC signal, one other thing you can do is you bias it with a current source. So the other thing, so IDC. So whether you bias it with a DC signal or a current signal, it doesn't matter, right? We just need some way to translate it into the correct class of operation. Because current and voltage are effectively do the same thing. You increase current, increase voltage, sort of thing. Now this can either be implemented, so this thing here is either with a current mirror. Do we remember what a current mirror looks like from 2133? Briefly. You might encounter it, but effectively it's just something which holds a constant, creates a constant amount of current. This might also look like, I think I saw in another past paper, it looks something like this. So that current source looks like this. Does anyone see how this might be a constant current source at the bottom? This one here. So this is separate. Yes, so VDC is constant and that value never changes. And so that's going to enforce a certain amount of drain current to flow. And that's in this position here. So it'll enforce a certain amount of current to flow through that, a DC current to flow through this amplifier as well, because they're in series, thereby setting the operating point of the amplifier. Yeah, so I think I've seen that in one of the papers as well. So something to be mindful of. Is there any questions on this? Yep. Yep. The input signal is input. So I'm just drawing the DC signal part of it, but I haven't drawn the AC signal part of it. The AC signal part would also be input somewhere here. Because it's not the AC that's the problem, it's mainly the DC. Good question. Yep. So that's so good. Yes. So that's if instead of applying a voltage, DC voltage at the gate to bias the signal, we're using a current now, a current source. So you might see either or in the papers. Cool. Any questions on this? If there's no more questions, then the next thing I wanted to move on to was timing diagrams for setup and hold time. So usually something which is pretty confusing. So setup and hold time. And one other thing I wanted to mention is there will be a break, so around the midpoint. So yeah, so after this, go through one question from the past paper, then we'll take a 10-minute break, and then we'll finish up the other past paper questions as well. Cool. So setup and hold time. So timing diagrams come up in the exams, unfortunately or fortunately. So the context I'm going to talk about it is in terms of a latch. So a latch is fundamentally comprised of a master and a slave topology. So not sure who chose this naming, but this is what we're going with. So master and slave topology, and they both have a clock signal, so clock. And then this has sort of an inverted clock signal. Okay, so let's fix that up. So they both get a clock signal. And then you have some input here and some output. Now the input is usually some input D, and then the output we refer to as Q. And so this is effectively what you might know as a latch. And so let me just quickly draw the timing diagram of what a normal latch looks like, and then I'll show what a setup or hold time violation may look like. So if you have a clock signal, some standard clock signal, like so, and then let's say I have some inputs. Let me draw it to make sure there's no violations. That looks good. And then maybe it's, yeah, that's fine. So some input that changes. And I'm assuming that the output starts off at a low state. So it starts low. Now, the way the latch works is that the output Q will only latch onto the input signal D when the clock signal goes high. So this is a positive edge triggered flip-flop. Latching circuit. And so what we have is at this point here, so at this point here, it rises, falls, but at this point it rises, but the input signal and the output signal are already both low, so it doesn't latch onto anything. It only latches on about at this point here. So at that point there, it latches on. And then the signal goes high like that. Okay. Is that okay so far? So just a standard sort of latching circuit, flip-flop type circuit. Sorry, that is, there we go. Okay. Now, the one thing to emphasize with this circuit is this is ideally what it looks like. So I've drawn it without any violations, but often an assumption we make is that the master and the slave are infinitely quick. But in reality, they take time to process the signals. So the master, the first thing that needs to happen is that the signal D needs to travel across the master. Now that might have some propagation delay of say 10 nanoseconds. Then it needs to process through the slave, and that might have its own intrinsic propagation delay. So as an example of what a violation might be is, let's say the input signal D changes, right? Let's say it changes. That needs to then be processed across the master, and it needs to be held at this point, right? But let's say that the input signal changes before the master can have time to process it. That would be a case of setup time violation, because we haven't actually given the master enough time to set up the signal ready for the slave. Right? So even without the timing diagram, that's the general gist of it. And then the hold time is a similar principle. We're not giving the slave enough time to hold on to the signal and pass it to the output. So what that might look like on a timing diagram, some simple thing. And so the signal is coming in, and let's say okay. So yep, I think it's a good diagram. What diagram do I draw here? Yep. Cool. Okay, so if I refer to this diagram, the quote-unquote setup time is the time between this signal here, the signal goes high, and the next clock signal that goes high. And so you can see here there's plenty of time for the signal to go across the master and get to this point here. Whereas now if I look at the timing diagram, so that was T setup, the setup time. Now if I look at this diagram here, how much time am I actually giving the signal D to travel across the master before the clock signal goes high? Not very much at all. So if, as an example, if this propagation delay, let's say it takes 10 nanoseconds to get through the master, then, and let's say this is 2 nanoseconds. So this goes high, and this goes high. Now, is that enough time for the signal to be processed by this clock signal, this high clock signal? No, not enough time, because we've only given it about 2 nanoseconds before the clock flips. But the master took 10 nanoseconds. So what might this look like at the output? So as a violation is nothing. Nothing happens because it hasn't had enough time to actually pick up that signal. Where it will now pick up that signal is all the way over here. So only all the way over here will it then pick up that signal. Because by that point, it's had plenty of time to get through the master. Okay, and so that would be an example of a setup time violation. And so very common in the papers, it says, can you identify a violation? That violation would be this region here. Because theoretically, if everything is perfect, it should have latched onto the signal, but there wasn't enough time for the master to process the signal. Okay. Does that make sense so far? Any questions? Cool. Now I just want to show a hold time violation. So I think I drew a nice diagram here. Yeah. So now let me just alter the signal a little. So instead of it doing this, I draw it here. So assume it goes. Yeah. Okay, that's good. So just very quickly. So both directions are important now. So often we think of positive edge triggered flip-flop as only the positive edge that we care about. But we can see that they are inverted signals and inverted for a reason. Because on the low clock signal is where the slave actually processes the signal. Right? That's why we use the inverted signal. So now let's carefully look at what's happening here. So as an example, we'll say, okay, this takes maybe 8 nanoseconds for it to go from here to here. So if I look at this signal here, so the signal is high, it's high, that's all good. But then what happens, so it's actually not a hold time violation. So this one sucks to draw. Let me go low, and then let's start again. So let's try this, and then, yep, that's good. Okay. Okay, there we go. Okay, so the hold time violation is just a bit harder to draw, but effectively, what we are looking at, so let's just ignore this one now as well. Don't care about that anymore. So we still have the setup time violation here. Sorry. We still have the setup time violation here. But now for the hold time, let's analyze what happens. This is a very common timing diagram you might get. So here the signal is high. So what does the output do? Latches onto it. So latches onto whatever the output is. And there's clearly been enough time for it to latch on, which is good. So no problem there. So it latches on. And then what happens after? So we keep going with the timing diagram. Anything happen here? Nothing. Nothing happens here. Still nothing. Does anything happen here? Yep. So let's say that's not long enough. So would it pick up the signal? Probably not. So keep going. So still nothing. And then I drew it too short. Sorry, bear with me. And then let me just draw a few more clock signals. Okay, so this is good though. We're going through a timing diagram, and then let's say the output goes, so now it's low. Will it clock on this edge signal? Yep, it will, probably will. Good. So the output stays low. So it clocks on this edge signal here, so it goes low. And then let's imagine the input signal does this. So I'll just line it up. So it goes high at this point here, and it goes low there. Ugh, it's a horrible diagram. Goes low. Let's say. So I probably shouldn't change the clock signal. Let me just change the inputs. I'm gonna make it a bit longer. There we go, that's better. And so it goes low. Okay, let's say that. Okay. Finally, okay, so now so I'll just spoil it. We do have a hold time violation. Can anyone see why? So let's imagine, so what happens at this point here? Yep, so it's already low, so it's gone low, good. And then what happens at this point here? Yep, just ignore it, and then good. And then what happens at this point here? So this is the setup time. So this region here, so the signal goes high, and we are now in the setup phase because the signal is going high, and the output is different from the output, which is low. So in this phase here, so at this portion here, what happens when we get here? Yep. Yep. Yeah, exactly. So as long as this distance is greater than 10 nanoseconds, let's just say it is, so we don't have any setup time violation. So that means the signal has successfully gone from here to here. That's great. Then, but that's not the full story, right? Because now, don't forget that the signal here has to be held and not change for 8 nanoseconds. So it has to be held here and not change. But if I look here, let's just assume this time from here to here is less than 8 nanoseconds. Does that look like a hold time violation? Yes, because the input has changed and hasn't been held here. So it needs to be held here for 8 nanoseconds, but it hasn't. The input has changed, which means whatever value is here is now corrupted and it's no longer what it was before, which leads us to a hold time violation. So what it actually looks like at the output is like, so it's like almost like it tried. It tried to clamp onto the value, but it couldn't. If anything, this actually probably looks more like something like this. That's what a hold time violation would look like, because it was set up correctly. There was enough time for it to be set up, but there wasn't enough time for it to be held for the slave to then take it to the output. Okay, does that kind of make sense? And so just for context, this is not specific to flip-flops and latches, this timing sort of notion. The notion of setup and hold time is consistent with anything which has timing diagrams. Often you have to set it up, and then it has to be held at some point before it's then processed to the output. And everything has delays. Okay. Was there any questions on this? This one here. I think as I rubbed that one out, that was probably not correct. So here there was a hold time violation. Here, there's not enough time for it to change. Oh, okay, sorry. I think here I just assumed there was enough time for it to change. Yeah, I just assumed that was sufficient enough time. That kind of. Yeah. So is your question like why it's increasing here? That is a great question. It should not be changing on the clock edge. That should probably be somewhere like here. I think it's just, yeah, the way I drew it was not fully to scale. Yeah, so like it should change, you're right. It should change here. And then it changes there. Good pickup. Does that make more sense? So now it goes to high on a clock edge. So the clock edge goes high, the output was low, and the input was high, and so it latches onto the high on the clock flips. I think that was because I redrew the clock signal, unfortunately, to what I drew before. But no, it should not have changed. You're right, it should have changed around this clock edge here. Should have changed somewhere around that clock edge there. And it would have just picked up to whatever this signal was, because that amount of time is not long enough for it to change signal. So it would have just picked up to whatever that signal was there. Mm-hmm. So when the clock edge is high, that's when the signal is going from D to the output of the master. Then when the clock signal was low, that's when it travels through the slave. But it starts its transition. That's why it's always a slope, because it starts its transition once it's processed here. And that's why the violation looks something like this, because it's almost like it started, but then there was a hold time violation. So it starts its ascent on the clock, on the high clock edge. No, because it's just the same thing but inverted. So because I didn't draw the inverted for the clock I didn't draw the inverted clock diagram, but it's the same clock signal going to both. If that makes sense. I think it's just a bit confusing. I didn't draw the inverted clock diagram, but effectively you have the same clock going to both. No, it's a good question. Good point. That's okay. Any questions on that? All good? Cool. So definitely quite a confusing topic, which is why I wanted to go through it. I definitely recommend you draw the timing diagrams yourself and go through them. Evidently, I'm not the greatest at drawing timing diagrams myself, but you can always look up timing diagrams online and try and analyze if there's any violations in those ones, and also pretty common in papers as well. But effectively, it's just to do with this propagation delay through the master and slave. Okay. Cool. Are we ready to go into the first question? The past paper? Cool. We'll take a break after this question. So the paper I'm going through is for the 2025 final exam. So I'm going to go through all three questions. Now, the first question is shown here. So figure 1A shows a highly accurate clock generator based on a crystal and a PLL chip U1. A partial datasheet for the NB3N502 can be found at the beginning of this exam paper. Some known circuit parameters are shown in figure 1B. Now, this is very common. The first question or the second question usually always has a datasheet associated with it. So it's good to get familiar with how to read a datasheet. But the first question mentions, the second part of the question mentions, the crystal resonance frequency is given below, where Lx is the equivalent crystal inductance unknown, Cx is the equivalent crystal resonance capacitor, C0 is the crystal self-loading capacitance, and Cin12 is the input capacitance of the NB3N502 on pins X1 and 2, and we're given some formulas. Now, again, just at a high level, it's quite intimidating to look at questions like this, so I'm going to give a lot more detail than is necessary if you were writing this in your own exam, but detail that you should be writing when you're studying for the exam. Okay, so the first thing I want to go through is what that PLL chip is doing. So question one. So part A. So the basic PLL takes some input frequency F in, And for context, the PLL here is acting as a clock generator. That's what it's doing. And I'll explain why it needs a crystal. So let me just draw it out. So the low pass filter is just to smooth the signal, doesn't have significant impact. And then we have a VCO. And we take this back, and it's, oh, sorry. There's usually some sort of division or multiplication here. And this is the output signal. Now, this is a standard PLL. Technically, the PLL is just what's in the forward path with the low pass filter and the VCO, and then to generate a divided frequency signal, we have that 1 on M in the loop. So these signals here, this has an associated phase F in, this has an associated phase F phi out. This is just your standard low pass filter. So just your standard low pass filter. Now your VCO is very important. So the VCO is a voltage controlled oscillator. So if I draw a graph of it as input voltage as a function of frequency as a function of input voltage, sorry. Sorry, Liam, the laptop turned off. So it's just a linear voltage controlled oscillator. So as you increase the input voltage to the VCO, the signal that comes out increases in frequency. Okay. And so now how does this actually functionally work? So this error signal compares the input signal, F in, to some reference signal at the output. So this signal here is F in multiplied by 1 on M. F out on M. So it's the output signal, and it traverses through the output and is compared with the input signal. And what's generated over here, let's go to this. What's generated here is what we call the error signal. So if you've done control, that seems very familiar. So this is the error signal, and it's functionally just comparing. So it's comparing the input and subtracting it with the output, the divided output. Now the desired error signal, so this loop will continuously run until that error signal is 0 because it's subtracting it away. So it'll keep running until this hits 0. And so if we work backwards from this as to what the ideal relationship looks like between the input and the output, in the ideal case where the error signal has gone to 0, then what we're left with is the output signal on the input is equal to the input signal. And so therefore the output is equal to M times F in. Now I'll explain more how it physically does this, but just as a general overview of what the goal of the PLL in this case is it's to multiply the input signal by some integer number. So if you want to double the frequency, triple the frequency, etc. And the way it does this is it utilizes the VCO as sort of an actuator to push that signal into one particular direction. So let's imagine the error signal is positive. So we have a positive error signal that passes to the low pass filter, which just smooths out the error signal, and then it goes into the VCO as an input. So let's assume the steady state of my system is, let's say here. Let's say this is the steady state signal, which will indeed give me a 0 error signal. So if the output is too high, so if I have a positive error signal, so let's say I have a positive error signal here, that positive signal goes here, and that increases the input signal here. So that means this increases slightly in frequency. So slight increase in voltage leads to a slight increase in frequency. Then that traverses through here and is compared again. And so it's effectively just comparing it and saying, has this slight increase in frequency made the error signal more towards 0? If not, we need to do further correction, and then it tries to correct it again in the loop. Let's say it's overcorrected and now the error signal is negative. That means a negative signal goes here, or a smaller signal, sorry, not just a negative signal, pushing the VCO slightly in this direction. And so we're just pushing the VCO slightly into different operating points until we have achieved an output frequency that is the input frequency multiplied by some integer number. And that's the overall goal of the PLL. I do recommend going through the maths. It might make more sense, but effectively that's what it's trying to do. So it's acting as a clock generator that locks onto one particular frequency. Okay, well, was there any questions on this? Okay, cool. The other building block we need is a crystal oscillator. Now, where the crystal oscillator is used is for this input signal here. This input signal has to be extremely precise. And crystal oscillators are probably the best way to get a precise signal. So what does a crystal look like? So often on like data sheets, it's called an exciton, like this. Doesn't matter too much. Now a crystal is, has anyone seen what a tuning fork looks like? It's effectively a vibrating tuning fork. That's basically what it is. So it vibrates, so it's a piezoelectric actuator, effectively is what it is. So it relies on vibrations to generate particular frequencies and particular resonances. And it's highly precise. I think one of the frequencies you can get down to is like 32.3479 something, 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 but it can get to a highly precise frequency. And how does it work? So effectively you have a capacitor, an inductor, and a resistor like this. And then you have a capacitor parallel. So this is C1, L1, R1, C2. And maybe this is your input and maybe that's your output, like that. Now, C2 is a very, very small number. So you can imagine you have two legs of your tuning fork. There's just a parasitic capacitance that sits between those tuning forks. And this is just an electrical model. The actual crystal doesn't have capacitors and resistors and inductors. It's just mechanical vibrations. That's modeled as an electrical system. So if we take this, so just as a note, C2 is much smaller than C1. So at really low enough frequencies, this doesn't really matter. At low frequencies, C2 looks like an open circuit anyway. So the only resonance we're focused on is a series resonance between these three components. So if I draw as a function of frequency, the impedance, so that would be the impedance along this line. So what happens as we get closer to resonance, to the impedance? Goes lower. These inductors and capacitors, the phase of them is in such a way that they effectively cancel each other out, so that impedance doesn't exist anymore. So we have a series resonance, so F series, so we have a series resonance that is somewhere here, that dips like that. So that's our series resonance point. And I have not drawn this to scale. In reality, the crystals are highly selective. Their Q factor is enormous. It's much, much greater than 1, so not this wide. So extremely selective, which is what we need for our PLL. We only want it to generate one frequency. But that's not the whole story. So what actually happens after this point? So maybe to make it super clear. So at resonance, the impedances equal each other, right? So the capacitive impedance and the inductive impedance, they equal each other. But what happens after resonance? What happens after resonance is that the inductor impedance is going to grow larger than the capacitive impedance. So grows larger. And that's just purely just by the maths of looking at it. On one side you have a fraction, one side you have just a straight linear increaser. So that means this entire thing begins to becomes inductive, mostly inductive. That capacitive is mostly ignored at higher frequencies. And so that means that this inductive relationship here interacts with this parallel capacitor and gives us another resonance. So we have another resonance that actually sits up here, which I'll denote as F parallel. Now this resonance, let's move this over. This resonance looks something like this, and then it decreases. So trying to draw it more selective. Okay, whatever, that'll do. We get the point. So you effectively go between a series resonance and a parallel resonance, and that parallel resonance has the formula. F parallel equals 1 on 2 pi square root of L C2, right? So it's dictated by those two resistances. So from here to here, so from here to here, we are capacitive. Then from here, from this region to this region, we are inductive. And then again, because that capacitor is a very small number, it's going to effectively look like a short at high frequencies, and so it's going to dominate. All the current is just going to want to go through that capacitor there. Sorry, no. No, that's not correct. Oh no, actually it is. That becomes capacitive. So the parallel capacitance then dominates, because in series, so because this was a case of series resonance, the inductor dominates, but in parallel resonance, the capacitor dominates, which leads us to this sort of impedance behavior as some other resonance. Now, so every crystal generates two resonances, a series resonance and a parallel resonance. Okay. Now, what's important for the question especially is that we put load capacitances here to vary the value of these resonances. So we can vary where these resonances are, depending on whether we're using the series or parallel one, just with these capacitors. Okay, and so if I go back to the question now, so I go back to the question, we have this formula, let's see, so we have this formula which we just wrote, which was that series resonance, and then we have this formula here, which is that normal capacitance which is in the crystal, plus some load capacitors we've placed on the left and the right, to give us a different equivalent capacitance. Okay, and we're just applying this on a PLL chip. And if we go look at the data sheet for the PLL chip, what do we see? We see the divider by M, we see the voltage controlled oscillator, we see the feedback, some sort of phase detector, which was the plus or minus thing I wrote, and then our crystal oscillator. And that's functionally what we're doing for this question. Okay. Was there any questions so far? Oh, good. Okay. So thankfully, the actual questions themselves aren't this long to go through, just to provide some context for the question. So then the next thing we need to do, a lot of calculations in this one, so I'll just get my answers ready. Cool. Cool. So let's look at part A. So the nominal crystal resonance frequency, so what it normally resonates at, is specified to an accuracy of plus or minus 10 ppm, or in other words, 0.0001 megahertz, when the total N2 node capacitance, so that is that capacitance there, is 16 picofarads. Find F naught for C2 equals 0 farads and comment on the result. So I guess what this question is asking is, can we get away with not including that capacitance C2? Will we still be accurate enough to be within that specified accuracy range of the PLL? That's what we need to test. So we have the nominal frequency, resonance frequency. Now we need to find the new resonance frequency without this C2 capacitance. So nominal capacitance just means the usual capacitance. So using the formulas we have, so the one formula we're given is the nominal capacitance is Cx Cn2 nominal over Cx plus Cn2 nominal. Now, one quality of life thing we can do is this just looks like a two capacitors in series. So Cx plus 1 on Cn2 nominal inverse. So just a quality of life sort of mathematics thing. And then what we can derive is the nominal frequency is, we look at the question. So the nominal frequency is here, or just the frequency formula, but we need to write two different frequencies. The first frequency formula is 1 on 2 pi square root of Lx C EQ nominal. And then the other frequency formula we have is just the standard frequency, which is 2 pi square root of L C equivalents. And then, so what we want to find is what is the value of F naught. Sorry, F nominal. We want to find, yes, F nominal. Let me check. Yep. So then this, so I can just divide these two. So there's, I mean, you could either do substitution or just subbing them in, but I'm just going to divide them, and that yields, so if I divide them, it'll be 2 pi. So this question is just a bit of math. It's a bit tedious. Not much for me to talk about. 2 pi. And so this will cancel with this. The amount of inductance on both is the same, so that'll cancel with that. And we are left with square root of C EQ over C EQ nominal. Is that correct so far? Yep, looks good. And then therefore the nominal frequency is F naught multiplied by CEQ on CEQ nominal. Okay, so good so far. And we just derived formulas for these capacitances up here. So this is CEQ nominal. CEQ will have the exact same formula, but just with C into rather than C into nominal. Okay. Any questions so far on this? Feel free to just yell out if there's anything. Just tedious math. Square roots of 1 on CX plus 1 on CEQ plus 1 on C into nominal. Like that. And then we are given that this formula here, so let me just move this down actually. So we're given that the C, to calculate what CX is, what CN2 is, CN, so that's just using that formula. To calculate what this is, that we are given that the equation is there. So do that. That is C into plus C out on 2. And this is assuming that that capacitance C2 is equal to 0. Was it? Yeah, either C2 or CF. I can't remember what they called it in the question. Yeah, C2. So assuming C2 is 0, and then you calculate that this number is 12.43 picofarads because we are given what the output capacitance is and we're given what the input capacitance is as well. And so then this is, when you calculate this number, yeah, I actually don't have it written down. I think it's, I think it was something like 10 megahertz plus 60 ppm, where 60 ppm has that frequency conversion of it being like 0.0006 or something. Now, just a lot of tedious math, but what's important is this final result. There's really nothing hard about just the equations. You're just subbing in some numbers, but it's the analysis that's really important. So we've set C2 equal to 0, and we have a deviation from 10 megahertz of 60 ppm. Is this allowable? Is this okay? So let's go back to the question. So it's specified to an accuracy of plus or minus 10 ppm. So we are outside the frequency range. Even though it seems like a very insignificant amount, these PLLs and crystals are highly specific. So I guess the comment you would make there is that this would not be okay. We can't set C2 equal to 0 farad. We need a bit of loading capacitance in that PLL. Okay. Any questions on that? All good? Okay. So the next few questions are a lot more interesting. So the next question, part B. So show how to configure U1 to give an output clock frequency of F clock equals 30 megahertz. So we currently have 10 megahertz. Any ideas? Yes. Mm-hmm. Yeah. Yeah, exactly. So when in doubt, always look at the data sheet. So it's a clock generator which has, so if we recall what I looked at here before, it's really important in reading time to just read through the data sheet and get an idea of what it gives you before you actually go into the question, because then you can sort of backtrack what you read in the reading time and remember, oh, I saw this on the data sheet. Okay, so because if I looked at this, I would have remembered it has a multiplier select, meaning I can select what frequency. And so if I just scroll a bit more this way, I can see there's a multiplication select table. So we needed a multiplication of 3 times. So that's looking at the 4th row. So S1 needs to be set to open and S0 needs to be set to ground. So that means I just need to set this to open and this one to ground. So if I go back, if I have my oscillator and then I have S0. And so for context, we're going from F clock equals 10 megahertz to F clock equals 30 megahertz for a multiplication of 3. Okay. And S1. And so S1 we set to open. So I'm looking at this column here. This one we set to open. And this one we set to ground. Was there any questions on that? So it seems like a pretty simple question, but the difficulty is knowing where to look. So knowing when to rely on the data sheet and when it's a good resource. And that's about it for that question. So let's look at question C. So part C. Okay, so question C is very interesting. So question C says, in the following, it is assumed that the PCB for the clock generator is double-sided, with the bottom layer being a ground plane and all components surface-mounted on the top side. It is further assumed that the U1 package is approximately 5 millimeters by 5 millimeters. The C1 and C2 packages are approximately 1 millimeter by 2 millimeters, with terminals on the short sides. And the X1 package is approximately 2 millimeters by 3 millimeters, terminals on the short sides. Sketch how to place and connect U1, X1, C1, and C2 to minimize parasitics on N1 and N2. So a nice PCB question. Let me try and break down what this board looks like. So effectively we have, so it's a 2-layer board, something like this. And there's another layer on top like this. So it's a 2-layer board, which I've exaggerated. So I've sort of like stretched apart the 2 layers. So this top layer here, that is your signal layer. And then this bottom layer here is your ground plane. So in reality, again, there's not this much difference between the 2 layers. They're sandwiched together, but we have 2 layers. The components go on the top layer and the ground is on the bottom. And as a side view, it looks like this. So signal layer goes here, like so. Now, really importantly, the purpose of a ground plane, do we know what the purpose of a ground plane is? Why do we use a ground plane instead of just using ground points? Yeah. Yeah. Yeah, no, that's 100% correct. So it's just to minimize the return path for ground, to minimize impedances on those return loops. So the beauty of a ground plane is wherever I need ground, I can just dig down to it and I have ground. So what we use in a PCB, it's too much, is we use what's called a via. So this is a via for access to ground. Okay, so we have our 2 layers and then a via which we can access to ground. Is that okay so far? Any questions? Ali, maybe just turn the laptop on. Yeah, just want to check if there's any questions online. Cool, all good. Awesome. Okay, so we're here now. We have our ground plane. Now we need to analyze where the parasitics are because that's what the question is asking us. So if I were to make a PCB, let's just say I was to make a sloppy PCB, and I had my capacitor here. So we were given a capacitor C1, and then the PLL chip or the clock generator I put down here, and it has 2 inputs. Now let's say I route this trace like this. So this is my routing. So what's also good about routing a PCB like this? So I wanted to go from one end of C1 to the clock generator down there. What's not good about this iteration of PCB? See someone shaking their head? I promise I don't design PCBs like this. Super long. Yes, so it's maximized. So why is that bad? More inductance along the line. So our goal for the question was to minimize the amount of parasitics on one of the nodes. I've just added lots of parasitics with this very long trace. So you had your hand up there? Good question. So not necessarily. Where these sharp corners matter is at RF frequencies. So when you're getting into the gigahertz or megahertz, like hundreds of megahertz or gigahertz range, then these sharp corners really, really matter. Because remember, at the higher frequencies, the signal is now more of like a wavelength rather than just a constant signal. So the way that wavelength propagates across this PCB really, really matters. So generally at RF frequencies, you try and have 45-degree turns in your PCB traces. Yeah, so lots of parasites, lots of inductance along here, very bad. Another thing that is also pretty bad is there is capacitance sitting between these two layers here. Anywhere you have two pieces of metal close by, there is parasitic capacitance. So parasitic capacitance there, not so much anywhere else, but mostly just, yeah, lots of parasitic capacitance sitting there. And so the obvious fixes there are to make sure you have very short return paths, and you also don't try and loop around like this, because there's also the EMI problem of if there was, for say, components here, then I might have formed sort of like a board loop, which increases the amount of magnetic interference. Cool. The other probably more critical form of parasitic capacitance is between the two layers. So again, you have two metal layers. Naturally, a capacitance is going to form between them. So you're going to form a capacitance from this top layer here all the way down to this bottom layer here. So you're going to form a parasitic capacitance. So C parasitic. And so if I was to draw that here, it'd be like that. That is the C parasitic. Now, this parasitic is quite detrimental, especially for the crystals, which we needed to remove the amount of parasitics near the node. But one thing to keep in mind is that this capacitance has the formula C equals A epsilon naught on D. So where this capacitance is coming from is because of the area of the PCBs and the distance between the PCBs. So how can I minimize this parasitic capacitance? Sorry, who said that? Yep, exactly. So reduce the area. So under any particular node where we're really concerned about this parasitic capacitance, we just remove the ground plane around it. That ensures that there's the return path from here to the next, to wherever the ground is not directly underneath. So there's no capacitance directly under whatever node we want to reduce the parasitics of. Does that make sense? And so I'll draw the PCB that it's asking for. So let's just go back to the question now with all of this in mind. So sketch out to place and connect U1, X1, C1, and C2 to minimize parasitics on N1 and N2. So with all of that in mind, let's draw the PCB. So the first thing I'll draw is, so if we look at the question, so we have C1, C2 are here. They need to be connected to two nodes X1 and X2. And we also need to connect it to, I think that was it. So U1, X1, C1, and C2. Yeah, with X1 being the actual crystal itself. Okay. So we have 4 components to draw on our PCB. So how can I draw this? So U1, let's draw here. So U1. And then it has 2 nodes there. So I think they were pin 1 and pin 8 or something. Doesn't really matter that much. And then we have our crystal, the crystal sitting here. Not to scale of what was mentioned. I can't remember what the scale was. So that's X1. Okay. Now, what's really important with a crystal and any differential signal is that you keep the traces on both sides identical. They must be identical. So in this crystal, because it's a really precise oscillator, the parasitics on both return paths need to be almost identical. If you're carrying any differential signals on a PCB, they must be identical. The trace lengths must be identical. The amount of parasitics they encounter must be identical, because it's differential signal, effectively. So that means, that's why I've sort of drawn it in the middle like this. So it's sort of equidistant between both of those pins. Then it passes through a capacitor. Now again, I'm going to place this capacitor as close as possible. I think like here's good. So C1, and then I have another capacitor here, C2. And another question I was asked is, how accurate do you need to be in your drawings? Just accurate enough to get your point across. This is going to be supplemented by some writings of the things I'm saying will actually go on your exam paper. Just enough to supplement what you're trying to say. It doesn't have to be super accurate, okay? So you don't have to draw the actual lengths of everything and all that. That doesn't matter too much. So then if I draw this, so I have I have a signal that goes to this capacitor, like that, and goes to the crystal there. Like as an example, the trace length the width doesn't matter too much, because that depends on other factors, but it's not relevant here. So there, and then there. And so I've now got my signal. So this is just the top layer of the PCB. You can see I've minimized the trace length as much as possible. And you would write this obviously in your paper, minimize the trace length. I don't have any weird corner interactions between different traces, so there's no parasitic capacitance there. And I've also made sure the crystal is equidistant between both of them. The other thing is now the ground plane. So if I imagine this is a part of the ground plane, and what we mentioned was to reduce the area, I can just make a cutout of the crystal. So I cut the ground plane underneath the crystal. So that's a ground plane cutout. Okay, so just cutting out the ground plane underneath, and so now the area of that capacitance between the two boards under the crystal has been effectively neutralized or minimized as much as possible. Okay, was there any questions for this? All good? Yeah. Oh, actually, good point. There needs to be a ground plane where we need ground. So where we actually need ground is for this crystal. So underneath most of this crystal, we don't actually need ground, but you made a good point. We actually need ground for this on this capacitive leg here and on this capacitive leg here. So I can't make the ground cutout there. It needs to be just before. So maybe there. That would be good enough. And then here is where our via would go. So that would be a via. That would be via to ground. Yeah, probably, but I think in this case we're just focused about these connections. I mean, I guess it's the case of like, okay, maybe I should shift the cutout, like depending on what the ground pin for U1 is, but this is as much as I need to get my point across for the circuit connections I've been asked to connect. Yep. Cool. Any other questions about PCB? All good? Cool. Okay, next question. So in the following, it is assumed that RL equals 500 ohms and CO equals 50 picofarads. The U1 clock out output resistance in the high state is denoted RH. Estimate RH and hence find the clock voltage in its high state. So maybe let me just sketch what it's talking about. So it's referring to the clock voltage being in its high state. And anytime we're in a high state, you should immediately think something's being pulled to high. Right? If we're in our low state, internally the chip is being pulled to ground. Okay, so part D. So what this looks like is a resistance RH, VCC, and then this is all inside the chip. So that cutout is where the chip is. So that's the chip U1. And then at the output, we have a resistor and a capacitor. So this is our LCL. And there's also some voltage here, some output voltage. And there is an output high current. And so it's asked us to estimate the value of RH. So where do I go from here to estimate the value of RH? Yeah. Mm-hmm. Yeah, exactly. And where can we get the output high voltage from? From the data sheets. So we look at the data sheets and we look for the output high voltage. That would be here. So we see it's 2.4 volts at 25 milliamps. Now, if minimum, typical, and maximum are given, usually we design for worst case. So always pick the worst case. That worst case might either be the minimum or the maximum value. Just have to use your judgment based on the context. Cool. And then if I go, so then we can just calculate VOH. VOH as VCC minus, RH as VCC minus V output high over so, and then VCC is 3.3 volts over minus the output high voltage, which was 2.4 volts over the input high current, which was 25 milliamps, I believe. When you do this, you get, have a look, 36 ohms. Cool. And then it also asked us to find the clock voltage, which since we know RH, how can I find the clock voltage? The output clock voltage, so that's this voltage here. That would be for the frequency, but it's just asked us for the clock voltage. So even simpler. What can we do? That would give me the voltage drop across the resistor, but I'm interested in just one particular node voltage. Yep, so yeah, so there's a few ways you can do it. One way would just be voltage division. One way would be to do it to the right. So take the voltage drop across the resistor, but now just look at what's happening at the right of the resistor. A few different ways you could do it. All of them would give the same result. The V clock is equal to VCC multiplied by, because it's effectively just a voltage division between these resistors here, right? Because I know VCC and I know what the resistors are, so it's VCC multiplied by RL on RL plus RH, and that yields 3.08 volts. Okay, Arlene, can you just turn the laptop? Sorry. Cool. Was any questions on that? It was given in the. Oh, okay, it's VDD, but it was given as 3.3 volts. Yeah, VDD, VCC, I think same thing. All good. Cool. All right, now next question. So, a 3.3 level CMOS digital signal, F control, is now to be used to control the clock signal, where the clock signal is 30 megahertz when the control signal is high. The clock frequency is 20 megahertz when F control is low. Modify the clock generator to include this frequency control. So before asking if there's any ideas, yeah. VOH is just specifically a node voltage. What do you mean in parallel? Question. I don't know if I'm confusing myself. That sounds right. So I just deleted the question. Have I drawn this fully correct? Yeah. Yes. I don't know why that was tripping me up. Yeah, that's correct. So it's effectively just VOH is the value when RO and CO aren't there, and then with some particular load, that voltage value will change because there's voltage division. Yep. No, good question. I don't know why it confused me so much, but yeah, it's good point to make. Yep. So VOH is the voltage when that particular load you're attaching isn't there, or it might be different to the load that's in the data sheet there. Yeah, good question. Cool. So going back to this question here, so before actually asking if there's any ideas, the one thing I like to do is sort of just map this out a little. So at face value, it's a bit confusing, but effectively what it's saying is if the control signal, if F control can be two values. Either F control is high or F control is low. So this is E. It's either high or it's low. And if it's high, then the clock frequency is 30 megahertz. And if it's low, the clock frequency is 20 megahertz. Okay. Any ideas as to how we can modify the clock generator so it has this? So we're given a digital signal F control, and we need to somehow modify the circuit we have so we can switch between them. So F control is either high or low. Yeah, exactly. So we look at the select function again, and we compare so in one case we need a 2 times multiplier, and the other case we need a 3 times multiplier. So we look at S naught, and what's interesting is that they both need to be kept to ground. So we don't actually need to do any control for S naught. We need to implement the control for S1. So to change between 2 times and 3 times, either we pull to ground or we leave it open. Okay, so no pulling to high. And so effectively what that looks like is you have the circuit here. So S, you have 2 control signals. And so which one was kept low? So we keep S naught low, S naught, S1. So this one is kept to ground. And then for this one, we have some sort of switch that pulls to ground. Some sort of switch that is effectively controlled by F control. Right? But now we need to actually implement this logic. So I just implemented it as a switch, but we need to take this a step further. How can I actually implement this logic? What could I use? Transistor? Yep, transistor is always a good switch. Which one? So NMOS or PMOS for the switch? Yes. Exactly. So you mentioned a good point. Now, PMOS sounds like a good idea because for a low signal, so let me just write it maybe more clearly. So for 3 times, we need to pull open. So for 3 times, we need to pull, this needs to be open, and this needs to go to ground. Now, you've raised a good point that if I use PMOS, it sounds like a good idea because a low signal needs to pull to ground. But does a PMOS pull to ground? No, only an NMOS will be pulling to ground. So we need some sort of NMOS with some sort of inverting logic to get it working. So I think first you identify, okay, I need an NMOS. And then as you just did, we work backwards to see how can we deal with that control signal. So what this then looks like is, so to S1, we need some sort of NMOS. That's a VDD ground. And so if the signal is high at the NMOS, it'll pull S1 to shouldn't look like that. So it needs to be open for a clock frequency of 3 times. So that means when the clock signal is high, it should just be open. So what did I do? I drew this incorrect. What is incorrect about my drawing? Yes. So how should it be drawn instead? To make it so it's open instead. Exactly. So if anything, nothing there. Right. So that when the switch is on, I initially just drew it wrong because I'm so used to drawing a VDD, but effectively we just want to leave it open when the signal is high at the gate, and then in the other option we want to be pulling it to ground. Okay. But the logic is inverted here because if the signal is high at the NMOS, S1 pulls to ground, but what we wanted is when it's high, it's pulled to open. So we need to invert the logic. So I just need an inverter sitting there with a control signal, like that. Does it make sense why I had to invert the logic? Just because we needed the opposite function. Okay. Was there any questions for that? I don't think so. I think a mux could also, because you really only need one control signal. Mux could work. Mux works equally as well. It's a good solution. It's actually a good point. Unless the question specifies the complexity, like saying make it as simple as possible, then yes. You can make this as complicated as you want. I think simplest solution is, yes, just a transistor.
It works now. I asked like the other members to check, and it was okay. I was checking the chat as well, and I think it's pretty decent. Do you want to use it? We'll be right back. Animation.
So who was watching this? Or someone outside? Yeah. Sorry if it was muted. Was it muted for long? Yeah. Can we just mute it for now? Yep.
I can head to work. Oh, my. Oh, okay. I'll be back. When are you coming back? I think yeah, we'll be done. Can you bring like a gift bag?
Yeah.
Possible. I think maybe in the office they might have like a small bag, even like a paper bag. Oh yeah. Did you get a bag or not? That's fine.
It's in my bag. I should have gotten one from home.
Yeah, it's all good. It's all good. No worries. Surely there's something at work. Oh yeah. Mate, wait, you got this limited. Oh yes. You have the time table, like you have to specify the timetable, so you have some sort of set up time between.
Is it going okay? Yeah. I meant like the first 2 hours. All good?
Yep. It's really interactive, so that's nice. Yeah, good. The mic.
I think it's connected.
I think it's connected with this.
Yeah. No, I think it's this one.
No, it's this one.
Both.
This is both. Yeah, I think it's a dual. Okay, I'll just leave it here if you need it. Okay.
Can you just check the volume?
Yeah. Again, boosted it.
Yep. Can you just check the chat to see? Is it Ash? Were there any comments on? Was there any comments on the stream? Yeah, regarding the muting more, or it's still okay? Okay. Hello.
I mean, it takes a while.
Yeah. Cool. Cool. All right, I think we'll get started again. Sorry, I think that was about 10 minutes. I just wanted to start a bit early, just so I could make a quick correction about something I said earlier. That was rightly pointed out to me. So when I was showing the flip flop, the timing diagrams were for a positive edge triggered flip flop, but the way I had drawn it. Oh, sorry. We need to get rid of that.
Yeah, I'll just full screen.
Okay. Yep. So the way it was drawn was for a negative edge triggered flip flop, so the clock signal should have actually been the other way around. The analysis doesn't really change if you just assume everything was for a positive edge triggered flip flop, which the timing diagrams were for. Just with the diagram itself, the clock signal should have been inverted the other way around. But yeah, the analysis doesn't change anymore. It's just a quick clarification to make. Yeah. Was there any questions on that as well? Cool. Okay, let's get through this question. So question 2. So a high gain DC coupled amplifier with offset calibration is shown in figure 2A. The offset calibration is implemented with RP1 and R4. Some known circuit parameters are shown in figure 2B. The circuit is powered from a plus or minus 2.5 volts power supply, and the operational amplifiers can be regarded as ideal unless otherwise noted. So the first thing to mention there is it says a high gain DC coupled amplifier. That means we're not removing the DC biasing from the input signal. So usually between amplifiers, you might see a capacitor. That's to block out the DC signal. Here, we're not doing that. And then, excuse me, we have a trim pot in the middle for calibrating away the offset. Okay, that's the context of the question. The right amplifier, as we'll see later, is used as a low-pass filter. Cool. So the first part, so the U1 input referred offset voltage is VOS1, while the DC output voltage is denoted Vout DC. Find Vout DC expressed in terms of the input voltage, the output voltage, VCC and VE, and component symbols. Okay. Now, just to, I guess, motivate why it's really important that we get rid of this offset. So what we have are 2 high gain amplifiers in series like this. So we have 2 high gain amplifiers. Let's say the gain of this stage is 100. the gain of this stage is 30, just arbitrarily, or even let's say this is a gain of 100 as well. Now, if I have some sort of offset on my signal here, so let's say some sort of VOS, then the output voltage is G1 times G2 times VOS. And so if this is 2 millivolts, then initially it's quite small, but then it has to pass through these two amplifiers. So then the output is 2 millivolts multiplied by 100 multiplied by 100. And you can quite quickly see that this input offset that started as 2 millivolts now will just saturate all of our amplifiers. So, and it's especially important because usually when you're using high gain amplifiers, it means your signal is already very low in amplitude. So we're dealing with very small signals. And so if we don't get rid of the offset, that means the offset is almost comparable to our small signal. So it's really important to calibrate it away, even if it looks initially quite small. Okay. How do you measure it? Yep. So to those online, actually, let me know if there's any questions online. But to those online, the question is about how we distinguish from really small signals to the offset and the noise floor as well, when they're all very small. It's a bit of a cop-out, but we use low noise amplifiers. We have amplifiers which are called low noise amplifiers for those specific purposes. So the noise floor on those amplifiers is quite low. It does mean to build those amplifiers, you have to sacrifice them in other areas. You have to sacrifice specifications in other areas. Like maybe it doesn't have as high bandwidth. But the noise floor is very low on those amplifiers. Like for instance, neural signals, their value is like 40 microvolts. Like it's very, very tiny. So we have to use very low noise amplifiers to detect those signals. But yeah, so this is a problem, so we need to calibrate it away. So we'll go to the question again. So find Vout DC expressed in those parameters. So Vout being on the right. So we have two stages. So the first stage just looks like a non-inverting amplifier. So I can kind of skip to Vx because Vx I know the relationship of. So let me just draw the circuit so it's clear. Okay, so I'll draw this circuit so we can keep referring back to it. So A. So we have some sort of offset voltage. Yes. Then R1, 2. R4. And then we have the trim pot here, so RP1. So up to this point, that is the first stage. And then this is pulled up to VDD. And sorry, that is not ground. That is some negative voltage VEE. And then we have, this goes into a second stage amplifier. That's R5. And then C2. Cool. And so the first stage here, so our input is here. Now, technically, this is V in plus the offset voltage. So whatever is being amplified at this point, so Vx is equal to V in multiplied by V in plus the offset multiplied by, what's the formula for this one? Yep, 1 plus R2 on R1. Cool. So we have that up to here. And now we need what this voltage is here. So that capacitor we can ignore simply because we're looking at the DC signal only. That's what it's asked us to look at. So it's basically open. And now the other thing to keep in mind is that highlighted here was a node Z. And what's the voltage at that node? So if we have an ideal amplifier, what's that voltage? 0. So that voltage is just 0, which makes our analysis a little easier. So we need to somehow get to here. And usually when you're in doubt about how to analyze a circuit, you just go back to the basics. You do KCL or KVL. So even if an amplifier you think, oh, it looks like something I've seen before, but I'm a bit worried about just using a formula, always return back to KCL and KVL. So here, I'm just going to do KVL at the node Z, because that'll at least get me to the next point. Okay? Even if there's a shorter method, just to be safe, I'll just do KCL. So if I just do KCL at this node, I have a current coming in here. I have a current coming in from the power supply, and then I have a current coming in from that node down to the lower power supply. And then there's also a current going that way towards Z. So I can just do KCL here, right? So the KCL there would look like, so I'll just move this out the way. And always in exams, try and make your life easier. I'm just going to call this thing V in. It doesn't really matter, just so I don't have to keep writing the offset voltage. So then what we have is Vx minus Vz on R3 equals, plus VDD minus Vz on RP1 being the trim pot equals Vz minus VE on R4. Have I left anything out? Yes, so then we have this current here, which I haven't drawn. So that one is just plus Vz minus V out on R5. Now, how can I make this equation a lot simpler? Yes, exactly. Vz is just 0. So gone, 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 gone. And all of a sudden, the equation becomes quite simple. So just move these around. Okay. So then what we have here is, do you guys want me to do this, or can I just skip to what this is? Yeah, just skip, right? So just, it's tedious. So then you get V out equals R5 on RP1, VCC, minus R5 on R4, VE, minus R5 on R3. So this was our previous equation that we derived, multiplied by V in plus VOS. Okay, cool. So that was that. So that's basically the answer for part A. Any questions? Just a bit of analysis, but I guess the key takeaway from this is if you're ever unsure, just do KCL or KVL if you're unsure about what it looks like. Cool. So next question. So RP1 is an 8-bit digital potentiometer with a resistance, so I'll just zoom out a little, is an 8-bit digital potentiometer with a resistance RP1 equals 20 kilo ohms multiplied by the bit number over 256, where B is given as that range, is its digital control word. In the following, it is assumed that, and we're given a formula, the offset calibration resolution, VOS in, is the smallest shift in the input referred offset voltage due to a change in B by 1 code when the offset has been trimmed out. Find VOS in when VOS 1 equals 0 volts. Any ideas how to start? I guess one thing that sticks out for me is the last part of that. So it says, when the offset has been trimmed out. How did we trim out the offset in lab 1? It's a bit of a throwback. How did we trim it out? How much do we remember? When I read some of your lab reports, it was pretty good. I saw you guys talk about this. So could we just measure it directly at the input, the offset voltage? No. Why was it difficult? So small. So what did we do instead? Yes. So we measured it at the output. We'll put a large gain on the amplifier, and we just measured it at the output because then it was a much larger signal. And then we didn't trim it in the lab, but we measured it that way. And then we just divided it by the gain to tell us what it was at the input. Okay. So if we look at this equation we've been given, so when the offset has been trimmed, because again, it's saying the smallest shift in input referred offset voltage due to a change in B when the offset has been trimmed out. So when the offset has been trimmed out, the only way we know it's been trimmed out is when the output voltage is 0. So if we look at the case where it's been trimmed out, that's gone. And we know it's been trimmed out because we've measured it and we've seen that the output is 0, right? For an input of 0, right? Because when we're measuring the offset, we ground the inputs because the offset is intrinsic to the amplifier. It has nothing to do with the input, so we just ground it. So that means effectively in this equation, when I'm looking at this, I can just ignore this and ignore this because that's when the offset has been trimmed out. Okay. Yep. So any questions on that so far? Cool. I think this one has numbers which I need to write down. Okay, so let me just rewrite that formula. There's also something else I'm point out in this formula. So V out DC is equal to 10 to the 4 times VCC. Okay. So as we just mentioned, so when VS1 is 0, so when that offset is 0, we know that was the case because B, however we trim that potentiometer with the word B, was trimmed in such a way such that was chosen such that but we only know this was the case because we also grounded the input. So what also must have happened was B in DC was 0. Otherwise, we don't know if it's the offset or our input signal that's being amplified. So with that in mind, then we have that. So rearranging this equation, and the way I came to this conclusion was it sort of gave me the context of the scenario. I based it off of that context, and now I'm just sort of logically following through on that. Because it asked me to look at the smallest change in resolution when we know the offset has been calibrated. So then I have V out at DC. Sorry, that's 0. So I have 25 minus 1280 on B. VCC is 0. So that's gone. So then I'm just left with B equals 25, 1280 on 25, which I believe is 51. 51. Okay. So that is the value for B, which the offset has been trimmed away. So for this value, the offset has been calibrated away. Okay. Or in other words, this is the value of B we need to calibrate away the offset. So it's sort of starting at the end result and then working backwards to answer the question of how we got there. Okay. So then I go here. And so what we need is to look at the smallest increment of change. So it gives us an example as going from like 100 to 101. In our case, it would be like 51 to 50 or 52 to 51. Okay. So we need to look at, so delta V out. So 25 minus 1280 V. So we're just looking at this portion, right? Because this portion here is effectively what our potentiometer is controlling. The first part is not going to change as I'm changing my potentiometer, right? It's just a constant input voltage. We're specifically looking at the change. So if I'm looking at the change, I can just ignore this. The only thing that will change with B is this part. So minus 25 minus 1280 and B plus 1. So that's my increment. That's my increments. Okay, it doesn't really matter, but I guess to give us a positive number, this should be negative and positive. Doesn't really matter because the absolute value is what's important. And so then when you rearrange this, you get that 25 cancels out and you're left with minus 1280 and B plus 1. And so then when we sub in our number, which we just found for B equals 51, we get 1.21 volts. But the question didn't ask for this. It asked for the input deviation. So how can I get to the input from here? Divide by the gain. And so what would be the gain? Do we see the gain in this equation? Yes, exactly. So it would be 10 to the power 4. So the way you can think about this is if I were to just use superposition, I just delete all the other voltage signals. So I delete VCC because I'm just doing superposition. Superposition of just the output and the input signal. So if this is gone, I just have A times my input signal, V in, right, plus VLS. And effectively that is just an offset anyway. So it's not contributing to the gain. So then to get delta V in, I get 1.21 volts over the gain, 10 to the 4, which gives me 0.121 millivolts. So I don't think the calculations are tricky. I guess the really tricky part here is just knowing what is the correct path to go down. I think for me, in a lot of questions, I always find starting at the end result easiest, and then how did we get there? Especially for a question like this, where it basically says, here's the end result, how did we get there? Which was what the question was asking. Was there any questions for that part? maybe as to why I did something or something? So good? Yeah, good question. So the question, Ash, is the mic still on? Okay. So the question for those online was, why did we set V in DC to 0? What was it, the output? V in, yep, the input. So the context we were given was effectively calculate a deviation on B once we have trimmed away the offset. So once we have trimmed away the offset, how much more offset are we going to get if B for some reason deviates a little? So if there's any maybe noise in B and it flicks one way, it flicks the other, am I still going to have a lot of offset voltage? And so just to, I'll come back to the question, but just to reiterate the endpoint, if I do have a slight deviation in from the point where I was calibrated, I will get an offset of 0.121 millivolts. So that's why it's really important to be precise. And so to answer your question, the scenario or the context when the offset voltage is 0 is when the input voltage is 0 and the output voltage is 0. So you can imagine when we're trying to measure the offset voltage, we ground the input, which is why input voltage is 0. Does that kind of make sense? It is a bit confusing, but effectively, we're only interested in the deviation from the calibration, because I guess a better way of framing it is, why would it be important to include V in DC? Yes. So that's why I mentioned when VOS 1 equals 0 volts. That's correct. So we're just saying when the offset voltage is 0 volts, the only way I knew this was the case was I grounded the input. And because the input was grounded, and the output is 0, that means I know I've calibrated away the offset. Because if the input was 0 and I was still measuring an output, that means I haven't calibrated away the offset yet. That kind of makes sense? Yeah. Oh, yes. Yes, that is a good point. So this VCC, that VCC, that would be times VCC. Yep, good pickup. Yep. Okay. All right, next question. So in the following, it is assumed that B equals 128. The presence of RP1 and R4 reduces power supply rejection in the amplifier. Recall that the small signal power supply gain is ACC equals the change in output over the change in supply. Find ACC and hence the amplifier power supply rejection ratio at low frequencies. So this is a pretty tricky question. So the context in which we're usually used to power supply rejection ratio, so this is B or C? Yep, so this is C. So the context which we're usually used to it is we have some sort of amplifier in the lab. So sort of amplifier, and then inside the amplifier are some transistors, etc. And then at some point we have an output. And then this goes up to our power supply VCC, and there's our output. Now, the power supply rejection ratio is a metric which tells us how well can the amplifier reject ripples on the power supply line. So if we instead treat this, rather than as just being a DC input, as something which has a DC offset with a bit of ripple around it. So if I treat this as some sort of offset, so that's my offset VCC, and then I have some delta VCC around it. So that value there is delta VCC. So we're looking at the AC fluctuations. Now, high power supply rejection ratio means it won't amplify that AC ripple. But why at high frequencies is this? Does the power supply rejection ratio go down? Remember why? What were the two reasons? I'm not testing it. It's okay. You can say anything. Do you remember from the lab? Yes. So one of the big ones is the gain of the amplifier itself goes down after the cutoff frequency, right? And so that degrades the actual amplification ability of the amplifier to amplify the normal input signal. Another one which is maybe not so obvious, but just as important, is that there is capacitance, parasitic capacitance all along this amplifier. So there is, so there's parasitic capacitance, and an actual MOSFET has a bulk there, and so then it looks like that. So I've drawn that bulk. That's not content in this course, but just to show where the parasitic capacitances are. Now, at low frequencies, this capacitance is not a problem, right? Not a problem at all, because it's such a small value that the impedance at low frequencies of those capacitances is so high. And so low frequencies are never going to want to go through those capacitors. But as the frequency increases, that capacitor starts to look like a short circuit. And so the signals are going to want to do this instead. So completely bypassing the transistors themselves, which were supposed to mediate this signal, to stop it from going to the output. So that means any AC fluctuations just does this and goes to the output and is amplified. Yep. Yes, yes. So good question. So, and the answer to that is it's probably the bane of every microelectronics engineer's existence is parasitic capacitance. It's like, honestly, a lot of the problems we face at microelectronics is because of the parasitic capacitance. It literally stops us from doing a lot of the things we want to do. But as something interesting, dynamic RAM is actually based off of parasitic capacitance. We use the parasitic capacitance to build RAM. So just as an example. But it's something we can't get around. At some point, we just start using it. We start using it as something physical. And you're right, it is really challenging. And I wish there was a good answer as to how you get rid of it, but it does depend on the value of the capacitance. So in a lot of modulation circuitry, like that was your example, right? So modulation circuitry, the capacitance there isn't super significant from what I understand. Like it does depend on the frequency. Yeah, it's a bit situation dependent, but there's no good answer as to how we deal with it. It's just, yeah, something which is which keeps a lot of engineers up at night, for sure. Yeah. Any other questions? Okay. So parasitic capacitance and its gain. So now we need to calculate the ripple. So we know that the gain of the power supply gain is dV out on dV in. So we're given a formula which is on VCC, because VCC is our new input. And so if I go back to this equation here, now instead of treating this as just some constant signal, now I'm treating this as sort of VC as a time domain signal. Right? So treating it as a time domain signal, and that means if I do superposition again, and I say now I don't care about the input signal, now I care about the AC signal at the power supply, then I can just ignore this, and I have a relationship of V out equals A times VCC, where this is my gain of my amp of the power supply. So then that now becomes my gain of power supply. So that was 25 minus 1280 on B. And they gave a value of 128, and so then that yields 15. Yep, that's 15. And then the power supply rejection ratio just has a very normal formula, AV on ACC. Yep, that's right. Of 10 to the 4, 15 equals 56 dB. And it mentioned the power supply rejection ratio at low frequency, so we don't need to worry about the cutoff or anything. Okay. Any questions to that? All good? Audio still all good? Cool. So next question. So the electrical noise in the amplifier is dominated by the U1 input referred offset voltage noise, which is white and has a spectral density of that value. The noise is band limited by the low pass filter implemented with U2. The total RMS noise of the amplifier output is denoted Vn0. Find the amplifier noise bandwidth and hence Vn naught. So what it's just saying is that the only relevant noise is the En noise for U1. All other noise can be ignored. So there's noise there, En, I. And that's the only noise we have to worry about. We have to worry about how it propagates to this amplifier. And it mentions as well, so it mentions U1 is a perfect amplifier, which means we don't have to worry about it. And the noise is band limited by the low pass filter implemented with U2. So that is this amplifier here. So that's essentially telling us we can ignore the bandwidth of U1 and say that the bandwidth constraint is coming from U2 to find the bandwidth then. So if we look at the formula for noise, and this is white noise, so it's not increasing or decreasing. Formula for noise, the out RMS squared is En squared inputs multiplied by pi on 2. And this thing is the noise bandwidth, which is often referred to as B, like that. Okay, and then, for context, the noise we're looking at is the noise that sits there on the amplifier, En. Okay, so we have our context set up. And then now we just need to find the bandwidth of the amplifier on the right. So the amplifier on the right looked like this. So we had a resistor at the input, a resistor in the feedback loop, and then a capacitor. And that one was R5, C1, R3. And so how can I find the bandwidth here? What can I do? What's a good way to find the bandwidth of this amplifier? So it's a low pass filter, yeah. So how can I find the formula for what the bandwidth is? Yep, so find the gain and the gain bandwidth product. Yep, but that is for, so there's two types of cutoffs here, right? So there's a low pass filter which is established because of this external capacitance. That gain bandwidth product is more so to do with the amplifier's own internal drop off. So two types of low pass filtering. So if I don't know where a pole location is, what do I derive? Transfer function, right? Again, even if it's the longest method, I know it's going to work. So I just derive a transfer function. And this one's really simple because what type of amplifier does it look like? If I just, non-inverting. If I just consider this whole thing as Z, then I have an impedance in the feedback loop and an impedance at the source. So it's just an inverting amplifier. So then you just do V out equals Vx times negative Z on R3, where Z is R5 in parallel with SC1, 1 on SC1. Okay, so we have that, and then I'm just going to skip actually subbing in all those variables, because then we just end up with R5 on R3. So V out on Vx is equal to on 1 plus S R5 C1. And then we know that every first order low pass filter has the exact same formula, right? It's just some gain A over 1 plus S on omega naught, right? You should have seen this in the filters topic. Stuff like this, I think, is also good to write down on your notes, different types of filters. It's just a first order filter where that is equated to that. And so we're left with F naught equals 1 on 2 pi R5 C1, which is equal to some number. But then what we're actually interested in is in the noise bandwidth, which is F naught times pi on 2, which is 15.7 kilohertz. And I think that's the end. Oh, okay. Then you can just sub those into the formula I wrote before. So you sub that into this formula here. We were given this number, and you can find V out. Okay, so then you're left with V out RMS equals 25.1 millivolts. Okay. Any questions on any of that? So the only tricky part was finding the noise bandwidth, but when in doubt, just go with the longest solution. Cool. All good? Okay. All right, so the next question is interesting. So modify the circuit to improve the amplifier's power supply rejection. Now, I find with questions like this, it's really important to be structured in your response and your thinking. So rather than jump to a solution, let me backtrack and think, what is actually causing the power supply rejection ratio to be low? That's the first question I need to answer, and then I can go to actually finding a solution. So one interesting thing is they mentioned in this amplifier, both of those are perfect amplifiers. So the power supply rejection ratio is not something which is specific to the internal problems of an amplifier, right? if there is some external dependency on the power supply that is somehow going into my circuit and being amplified, that's a connection that will amplify any ripples on VCC. And I think it also alludes to this in one of the questions. It says, in the following, so if we look at part C, the presence of RP1 and R4 reduces power supply rejection in the amplifier. Why might that be the case? Yeah, so we have, the problem is we have a connection. So even if we look at the formula that's down here, so even if we just look at this formula, we have an output that is dependent on, VCC, right? So that means any ripples in the power supply are going to be amplified by that gain there. So even though it's not the power supply rejection ratio problems we're used to, it's just some sort of connection from the power supply to the output that has a gain that will decrease our ability to reject ripples from the power supply. Okay. What are some ways we might be able to fix this? So if I were to just write this, so the problem we've identified is that there is a dependence on VCC. So we need to remove the dependence on VCC. How can we do that in the circuit? So maybe let me ask another question. What was VCC being used for? For trimming the offset. Good. So we're using VCC to trim the offset, so it's acting as a reference voltage. We're not really using it to power something, we're using it as a reference voltage. So what might be the logical conclusion from that? Yes. So one way, just as a logical conclusion to the questions I just asked, is let's use a reference voltage that maybe isn't as dependent on the power supply. How can we manage that though? Because that's tricky, because then if you want to generate another reference voltage, you need VCC. So what's something we could do? Yes. So one thing we can do is use a diode, which will clamp the voltage at a particular value, which means whatever reference voltage is now, let's say it's a 0.7 volt diode, reference voltage is now 0.7 volts rather than VCC. So VCC powers are on that diode, no doubt, but the specific value of reference voltage has nothing to do with VCC anymore. It's now clamped to 0.7 volts. So it's loosely dependent on VCC now. So I guess the takeaway from this is just the logical steps of, okay, here's the problem, here's what's causing it. Problem being that we're using it as a reference voltage, and so the only way to fix that is with a diode. Or there's other ways to fix it as well. So if I just draw it quickly, so one thing we can do, so if we have our output node here, so that's our output node, I think VZ, or just Z. So one thing we can do is R, and then we place a VCC, and then we place a diode, this to ground, and then we connect this as our reference voltage. So what we can see here is now this voltage, so the power supply powers on that diode, but it clamps the voltage down to 0.7 volts, and that voltage is what's being used as our reference to trim. So it has almost nothing to do with VCC anymore. VCC is just for the diode. And you would do the same thing on the negative side as well for VE, so because it has to be symmetric. But the other really important note with this is we want to minimize dependence as much as possible. So how do we choose this resistance value? Why did I put a resistor there? Yeah, so we're going to burn the diode, but what should be the relationship between R and RP1? Yes. So we need R because we want the bulk of the current to actually go through the diode, right? We only want a small amount of current to go through RP1. If a lot of current goes through RP1, that means whatever's happening at Z now affects this reference voltage. So we don't have an independent reference voltage anymore. And we don't want to form a voltage divider. So this current, so I say I1, I2, so we want most of it to go through here, so we'll call that I3. So you want I3 to be much greater than I2. Now there's no notes on power consumption here, so this might burn the diode, but it doesn't matter. We just need the current through I3 to be much greater than I2. so that, again, whatever's happening at node Z doesn't go back and affect that voltage. So then we just have, so we just need R much greater than, sorry, much less than RP1. Now, some other solutions I think I saw some students put last year was putting a linear dropout regulator. Now that's good for sometimes with power supply rejection ratio. So that's good for helping with minimizing the ripple on the power supply. But fundamentally, we still have the same problem of VCC being connected directly to the node. So it does loosely fix the problem, but it's not the main problem at hand. So that solution might get you partial marks. Yep. Mm-hmm. Yeah, so if you use some sort of like linear dropout regulator, the problem is it can't always, it doesn't get rid of all the ripple voltage. It's not perfect. Yeah, so that would, yes. Yeah, I agree. I think it's a good solution, but I think it still doesn't address the fundamental problem we have with the power supply. That's why I was mentioning it might get you partial marks. So it's still a good solution though. Cool. All right, so we'll move to any questions, or can I move to the next one? Question? Oh, just stretching? Okay. Cool. So the next question, okay, so this is the one I had in the presentation slides. A lot of these questions are actually pretty short, though, surprisingly, so which is good. So figure 3b shows a battery-powered system that drives a transmission line using an LVDS driver, U3. A low dropout linear regulator is used to secure a constant system power supply, BCC. A model for the LVDS driver is shown in figure 3a, while some known circuit parameters are shown in figure 3c. And so just looking at the context, effectively what's happening is we have a battery voltage. So we have a battery voltage here. It's going through a linear dropout regulator to regulate it to a constant supply voltage of 3.3 volts. That is powering a logic circuit, which is also powering a buffer, a driver. And then that is being transmitted across the transmission line to a circuit at the output here. Now, when we're transmitting signals, we always transmit them differentially. Does anyone know why? Yes, exactly. So we transmit them differentially so that, again, if one signal picks up noise, the other is likely also picking up the same amount of noise. So we can, and it's a difference amplifier, so we'll remove that noise that picks up. It's never a good idea to transmit signals with one reference to the ground and the other with just a signal, because then they pick up unequal amounts of noise. Cool. And the reason we coil them like this is just because the adjacent magnetic fields will cancel each other out. So this magnetic field and this magnetic field will cancel each other out. This magnetic field and this magnetic field will cancel each other out, which is why we coil them like that. Cool. So then it powers that transmission line. So let's get to the first question. So the battery voltage changes linearly from VB equals 4.1 volts fully charged to VB equals 3.6 volts fully discharged. When discharged with a constant current, it has a capacity of CB equals 2000 milliamp hours. U1 has a dropout voltage of VDO equals 0.4 volts. Find the system operating time with a fully charged battery TOT. Thoughts? Yeah, it is. Where would we start here? So maybe let's start by just drawing a battery curve and trying to contextualize the problem. Okay? So the problem we have here, so every battery curve looks something like this. Something like that. This is across time, that's the battery voltage. And so it has some sort of minimum voltage where it still functions. And then it has some full-scale voltage, which I think in this case was 4.1 volts. So this is a battery charging curve, and so this might be, so just as a random example, this might be 0.2 times the nominal charging capacity. And what really defines where the curve is how much current you're pulling out of the battery. So if I'm pulling, let's say 0.2 C out of the battery, it has a longer battery life, which is why the curve looks different. But if I'm now pulling, let's say, 0.5 times the capacity, then it looks something like this, right? So that might be 0.5 C. Naturally, because I'm pulling more current out of it over time, which reduces the battery life. Okay? And then if you want 1 C. Yeah, I'm just exaggerating. It wouldn't start exactly at 4.1 volts. So interestingly, it's slightly below. Yeah, I'm just exaggerating a little. Good point though. So this is our battery curve. Good. And then, sorry, that should be on that axis. The V minimum points should be there. Because on this axis we have T life. Okay. So that's our context. So we have some battery. And some charging rates. Now, the rate at which you charge and discharge a battery is really important. And as a fun fact, does anyone know why lithium-ion batteries always explode on the news? What is it about the battery that people do that's wrong? Yes, they overcharge the battery. So it's not specifically the battery itself, but they're charging it at a capacity that it's not rated for. So often when you're charging a battery, you charge it to C on 2, so half of its capacity, or you charge and discharge a battery. Really important for lithium ion to protect it. So often they get cheap chargers that are charging it at like 10 times the capacity, which it's not rated for. Cool. And also, this is important, I guess, for 3117 when you take it next year. When you're building a protection circuitry for charging, fundamentally what you're doing is you're limiting the charging rate. So you calculate how much current you're expecting to get out of it, and then you have a module in your circuit which limits it to that number. So it only pulls that amount of current for charging. Otherwise, you'll blow up your battery. Cool. So then that's the context of that. So charge changes linearly from 4.1 volts to 3.6 volts. When discharged with a constant current, it has a capacity. U1 has a dropout voltage. So the battery is here. It goes through an LDO, and we're using the LDO to drop the voltage or to regulate it to 3.3 volts. Okay. So, the LDO, so effectively what we're doing is we're taking this battery voltage, we are passing it through a BJT, an amplifier there, some reference voltage, and then, what does it look like? Something like this, I think, and then like that. And then we take our outputs there. Right? So R1, R2. Now, how this regulates voltage is not too complicated. So although we're not just regulating voltage ripple in this case, we're dropping the voltage, right? So we want it to be 3.3 volts. So this voltage is VREF as well. So we want our output to be, so the output is basically determined by this voltage division, right? So it's VREF multiplied by R1 on R1 plus R2. Oh, sorry. R2 on R1 plus R2. No, sorry, my God. VREF is equal to the voltage division of the outputs multiplied by R2 on R1 plus R2. And this tells me for any particular output voltage I want, how do I set the reference voltage? Okay. Now, is this much detail needed for this question? No, but it is needed for other questions, which is why I'm going through it. Okay. So if I want the output voltage to be 3.3 volts, then I carefully choose my resistor values and I get a reference voltage. Let's say the reference voltage is 5 volts, as an example, 5 volts. Right? It doesn't matter what specific value is. So if for instance, if this value, if the output voltage for some reason increases above what it's supposed to be, so the output is supposed to be 3.3 volts. Let's say it increases above what it's supposed to be. What happens then? So that output value, so this node also increases. So if the output increases, the reference voltage also increases. Sorry, not the reference voltage. This is not VREF. Someone should be correcting me. The reference voltage is up there. This is just some node Vx. Right? Just some node Vx. That in turn sets our reference voltage. So if that node increases, this node increases as well. And so VREF, if we just say is, so this is 3.3 volts. Let's say VREF is, I don't know, half of that, half of 3.3, 1.1. Thank you. I don't know why that was so difficult, but so 1. Okay. Okay. Cool. Yeah. So 1.5 volts. So if this, so normally this is, let's say, divided by half. So it should divide the voltage down by half. So this is V out on 2. But now let's imagine this slightly increases above 1.15. What happens to the output of the amplifier? Yep. So if this is high, then that means V minus is greater than V plus. Right? So then what would it do? The amplifier will output low. So it output low. So this outputs a low voltage. So outputs a low voltage, which decreases the amount of current being driven into the BJT. Right? So less current into the BJT. So less current. And so less current into BJT means less current this way, right? We're not pulling in, we're pulling less current into the output. And so if we're pulling less current into the output, so this current decreases. So less current being driven through the BJT means less current being driven into the output node, which decreases the output, right? Back to what it's supposed to be. Does that kind of make sense? Just a little? Was there any questions on that? How the audio works? All good? Okay, so that's just basically how it regulates. So it's basically a feedback loop. So then it decreases the output voltage here. Cool. So we're going to need this context as well because the dropout voltage is referring to is the dropout voltage across this transistor. So fundamentally, how the LDO reduces the amount of power is it dissipates it through that BJT. So it dissipates it through that BJT, and so and that also sets a limit because we need to keep the BJT on. And the BJT is only on if we supply enough voltage. I think in this case it's 0.4 volts. So VB minus the output must be greater than the dropout voltage, otherwise the LDO stops working because the BJT isn't on anymore. Okay? Question? Oh no, it can kind of be anything you want, just depending on how you choose those resistance values. I just assumed they were dividing voltage down by half. Yeah, it's just arbitrary. Cool. So we have to keep this in mind. So then if we finally go back to the question one more time. So find the system operating time with a fully charged battery. So it charges down to 3.6 volts, but we need a charging value of, it needs to charge down to for us to what? Yes, it can only go down to whatever the dropout voltage allows. So what I mentioned was the dropout voltage is equal to the battery voltage minus the output voltage. And a better way to write this is that the dropout voltage must be greater than or equal to the dropout voltage. So we can keep that BJT on. So VB was 4.1 volts minus the output, which is 3.3 volts. And the dropout voltage, we're trying to calculate what VB needs to be for this to no longer apply. Because that's the minimum we can, minimum battery voltage we can charge down to. So VB must be greater than or equal to V dropouts plus V outs, which is 0.4 volts plus 3.3 volts, which is 3.7 volts. Okay. So that's the minimum voltage we can charge down to before the LDO turns off. Okay. Then if we look at the lifetime of the battery, so what we're interested in is the lifetime here. So how long does that take? So we know what we know for this question. We're interested in finding this value, but we kind of have to extrapolate for the value. So one thing we're told is that we can assume that that part there is linear. So that charging down from 4.1 to T light is linear. So we have to extrapolate. So we know what we're given. We're given that CB equals 2,000 milliamp hours. That's the first thing we're given. And the way to find what our charging capacity is now, this new charging value, this charging rate, we just extrapolate. We say C effective is just C being multiplied by full voltage range over the usable range. Right? And so that's 2000 multiplied. So the usable range, what was the usable range? Yep. I think I have this calculation done somewhere. Yep. So it's the usable range is 3. So what was it again? What did we calculate it as? Yep. Exactly. So the full voltage range is 4.1 minus 3.7. No, sorry, 3.6 over 4.1 minus 3.7. No, that doesn't work, right? Oh no, that's right. And I don't actually have this calculation done for some reason, but it's some number. We just have to take that. It's some mysterious number, unless someone has a calculator. 1,600. Good, thank you. Okay. Then we know that the charging capacity is just. Where do we go from here? We know the charging capacity is defined by, so it's milliamp hours. So it's the amount of current we're drawing multiplied by the time. So if I just rearrange this, I get T equals C on I. And then we just derived our effective battery capacity. Remember, we don't have access to the full range, so we don't have the same battery capacity anymore. Okay? So then this is 1600 milliamp hours over. Now, in terms of the current draw, we are told that the current draw coming out of the LDO is 100 milliamps. So that's how much current we're drawing from the battery. So then over 100 milliamps gives you 16 hours. Okay. Is that right? Cool. Any questions? All good? Cool. Next question. So U1 has a junction to ambient thermal resistance of that number, while its maximum allowed junction temperature is Tj max equals 125 degrees. Find the maximum ambient temperature that ensures Tj is less than or equal to Tj max. So when it refers to the junction, they're referring to essentially where is the hottest part of the chip. And then junction to ambient is the resistance from the thermal resistance from that junction to the ambient air. While its allowed maximum junction temperature is 125 degrees. And so we're asked to find the maximum ambient temperature that ensures that the junction temperature is less than or equal to the maximum temperature that's allowable. Okay, so let's do this. So how might I start with this question? What's the first thing to do in any thermal question? Draw a circuit, yes. Torsten loves this thermal circuits. Should I get this right? Yes, good. So we have our junction to ambient temperature, so TGA there. And then so that's the junction. Show this junction, T junction. And then that there is T ambience. And then we have some sort of power draw. So PU1 is the power draw of the linear dropout regulator. That's grounded. And then we have the ambient temperature, which is just a voltage source. Okay, so this is just the electrical equivalent model. And so we're asked to find effectively the junction temperature. And so for that, we need to know what the power draw of the LDO is. So if we go back to the circuit I drew up here, what power is coming out of the linear dropout regulator? Or what power loss? Where is the heat dissipation coming from? Yes, the BJT. It's only coming from the BJT. And we're just assuming that there's no current here. We're just assuming there's no current. So we're assuming it's all coming from the BJT. So then the power dissipation is just VDO multiplied by, what would be multiplied by? The supply current, because that's how much current is flowing, right? Like the I supply. Right, so then that value is, I think I have that number here. So yeah, so P LDO is equal to VB minus V out multiplied by the current. And we already calculated this number, so I'm showing it a long way anyway. And here we want to calculate the worst case, because the battery voltage happens over a curve, but we want to calculate, because it's asking us to calculate what is the maximum allowable. So we need to calculate the worst case. What value for VB should we choose for worst case? 4.1. So VB max minus VCC times 100 milliamps, which gives 80 milliwatts. And then you can just do some easy circuit analysis. So you go TJ minus TA on theta JA, sorry, and that's just the voltage across resistance. And then rearrange that, and you just get TJ equals TA plus P1 theta JA. And then just rearranging this, and you get TA equals TJ max minus P1 max times theta JA. Okay. Is that okay so far? Just some circuit analysis. And then when you calculate this, you find it's 110 degrees Celsius. So effectively what we've shown is that under the worst case power dissipation, the ambient temperature can go up to 110 degrees Celsius, so that we don't violate the limit for the junction temperature. Is this a problem? Yeah, maybe, yeah, like under normal conditions in the lab, usually what, like 25 degrees? This is probably a problem if you're like in the desert or something. probably only about then. But otherwise we're okay. So part C. In the receiver end of the transmission line, R1, R2, R3, and R4 must now be found such that nodes X and Z swing symmetrically around VCC 2 and such that the receiver impedance seen by transmission line RL ensures that there are no reflections at the receiver. So with a question like this that says so many things, I like to break it down into each condition it's asking me for. So the first condition being, it must swing symmetrically, that's condition number 1. So it must swing symmetrically, condition number 1. Second number condition, it must be around that particular value. Third condition is that there must be no reflections at the receiver. Okay, so 3 conditions. So let's go through those. Okay. So parts D. So if I just quickly draw what the circuit looked like. So effectively we had this. And then we had a second driver that came from here. Like that. Okay. And then this went to one particular node here. R3, C2. And because the nodes are basically identical, to simplify the problem even further, I can just look at one of the nodes. Because you had the top node, which is X, and the bottom node, which is Z, but they have basically the exact same circuit. And we want them to be symmetric anyway. So R3. Now I can look here and I can go to ground R4. Okay? And that one is node X. That's all right. Thanks for coming. All good. Okay. So generally with transmission lines, why do reflections occur in transmission lines, just generally speaking? Mismatching impedance. Is this a problem at low frequencies? No, because at low frequencies the wavelength is very long or short? Long. It's like kilometers long. It means we don't really see it as a wavelength. Whereas at really high frequencies, what happens to the wavelength? It becomes really short. So now we have to consider it rather as just a signal, but as a wave that propagates through different mediums. It's like trying to push a wave from water to oil. Some of it is going to transmit through, a lot of it is going to reflect back. Okay? So that means the impedance, and we're told that the impedance across this line is 50 ohms, and we need to make sure that this impedance RL that's seen by the transmission line is also 50 ohms. Okay? So step number 1 is we need symmetry around VCC. VCC on 2, sorry. So if I look at this circuit, so now I need to go back, and it's a bit tricky here because now I need to actually consider what the buffer is doing. So this buffer in the top right, also the power driver. So the power driver, if A equals 1, let's consider the case where A equals 1. If A equals 1, then this path is connected, like that. So that path is connected. And Y, the conjugate, is pulled down to ground, like that. Right? So we have sort of a different currents flowing on each line of the circuit. So this would be, this output would be Y, and now output would be Y prime. Is that okay so far? Okay. So that means currents can go across this transmission line forwards and backwards, right? Depending on the signal we're trying to get out. Now let's consider what normal operation would look like. So under normal operation, if let's say A equals 1, then I expect that Vy is greater than, oh sorry, not Vy anymore. So Vy travels across to Vx, right? So under normal operation, I expect that Vx is greater than Vz. And the reason I expect that is because if I'm trying to transmit a 1, I also want a 1 to come at the output. I'm just trying to transmit it over maybe a long distance. So if Vx is greater than Vz, what happens to the amplifier? Yeah, so it becomes a comparator and just outputs a high value, which is what we want. So that's normal operation, right? But again, the problem is current can flow in and current can flow out. And we're thankfully told what the current is at that node X there. It's 10 milliamps. So with that in mind, we need to consider that it can flow this way, and current can also flow this way. Okay? So we can write an equation for what Vx is. So Vx is VCC. So what do we want Vx to be? We want it to be centered around that. How could I derive the equation here? So there's two parts of my equation. One is always try and use superposition when you have multiple voltages and multiple currents. So if I just ignore the current for now, what's the voltage at Vx? Yeah, it's just the supply divided by 2. So it's just VCC. Sorry, that's the answer. But before that, we don't know what R3 and R4 are, so it's just a voltage division. So R3 plus R4 multiplied by VCC on 2. Over to the mic. Yeah, cool. So it's just VCC on 2. Now let's consider with the currents. So what would the value of current be? So again, let's just use superposition, right? Anytime we have multiple voltages and multiple currents, so we have a contribution. So this we can think of as almost like the DC offset. Now we have a current being either injected into the node or being taken out. And so if I use superposition, what do I do to VCC2? Ground it. So now I'm just looking at what is IX. So IX, so if the top is ground, what's the relationship between R3 and R4? Parallel. So what would be the voltage at Vx then? Exactly. So Ix would be the current there, just multiplied by the parallel combination between R3 and R4. Okay. So plus or minus Ix, R1 in parallel with R3. So for symmetry, what do I have to enforce? Exactly. So all I have to enforce is that R3 is equal to R4. Right? Because it has to be, sorry, there's two conditions. So the first one being that it has to swing around VCC on 2. Right? So the only way, sorry, that should not be there. That should be, for some reason he's called this voltage VCC2, which has made things a little confusing. Good question. So, yeah, so the question was, what does it mean to be symmetric around VCC on 2? So, maybe let me just go back to the wording of the question. So, must mean such that nodes swing symmetrically around VCC on 2. So that means, so if you have some sort of voltage like here, and let's say the offset is VCC on 2, that means they swing in equal direction and equal proportion in both directions. So the high and low swings are identical. Yes, exactly. And also the symmetry that both this one and this one have to see the exact same swings. Yeah. So yeah, definitely confusing because there's multiple symmetries. Cool. So then if we enforce that condition, that's great. I think that's all for that one. Yep. Cool. So R3 equals R4, and we wanted it to be symmetrical. So if I go back to the question, I was only looking at R4 and, sorry, this should be R1. My apologies. I don't know where I got R3 from. R1. R1. And so we're enforcing currently R1 equals R1 plus 4. So what should I do? What should I do about the relationship between R2 and R3? So I've just said R1 equals R4, so I've just been looking at node X. Should I do the same thing to RZ, as to R2 and R3? Why? So it's symmetrical, right? Sometimes the simple solution is the best solution. So then I just say, okay, equals R3 equals R2. Done. Now the third condition, sorry, I've only looked at the first one. So the second condition is that RL must be 50 ohms. Right? How can I enforce RL equals 50 ohms? Exactly. So what it means by no reflections, it means the reflection coefficient is 0. So it's not too important, but effectively, what was it? Sorry, say it again. What did you say? Yes. Yes, exactly. So if we look at the circuit here, so effectively the resistance that is seen at this node here has to equally divide between both of those nodes. And so you said both 40? Yes, so both should be 50. Does it make sense why? Anyone have a different answer as to what it should be? Maybe 50 is not correct. Thevenin resistance? So why the Thevenin resistance? So what would the Thevenin resistance be? $25. You agree? 100 each? So we have three different answers. We have 50, 100, and 25. Who do we think is the right answer? Any other thoughts? So I guess it's a good point to sort of stop and think. So how do we choose RL? So as a reminder, we were choosing RL so that it is equal to 50 ohms. And so we need to find out what RL is. So what do you agree it's 100 as well or 50? Yep. Yep. Any other thoughts? Yes. So RL is supposed to be it's supposed, so maybe let me make it easier by redrawing the circuit. Exactly. Let me redraw the circuit. I think that'd be easier. Yes. So I can redraw it as one resistance here. So I'm just going to draw it sideways. So R1, and then you have your node Vx. And from the current condition, so I guess one thing maybe I skipped is that we need, this is the current swing for the node Vx, the current swing for the case of VZ is just going to be the same thing but with different resistance values. So this one would be, so R2 and R3. That would be the case for VZ, right? Just the opposite voltage swing. Sorry, R2, R4. Yes, yes, should be. Yes, there we go. Yes. No, it's R1. Oh, I had it right. Sorry, guys. Sorry, long 3 hours. So R3, R3, and then this one is R3. Yeah, so this is going a bit over time. So feel free to leave. It will be recorded, but it's good if you could stay. So R2, R4. And so these must be equal, which also enforces the condition that R1 equals R2 equals R3 equals R4, right? So if these are equal, then how can I redraw the circuit? So this one here was R1 in parallel with R3, right? And the reason for that is because we're looking for, like if we think back just to quad 1, when you're looking for what is the resistance looking into a node, what do you do to, what's it called? Yeah, what can you do to voltage sources? Could short them, right? That would, and when you short them, you find that the resistance is effectively just the parallel combination, right? So then where do you go from there? Yep. So what would the circuit look like? So it would look like R1 in parallel with R3. Yep. Also you have VZ R2 parallel with R4. And then what we're looking for, what we're interested in is RL. Now, why have I drawn them in parallel though? Yep, but even before that. Yes. So effectively, what we're looking at is, so we have a constant source here of let me redraw that, of, so the reason I've drawn it like this, so you don't have to draw it like this to see it, but effectively, when we're considering the impedance, we need to consider the interconnected nodes. And so I'm effectively connecting the nodes here. So this node here and this node here. Sorry, this one here and this one here. And that's VCC on 2. And I'm just drawing an equivalent circuit by dividing the voltage on 2 because that's how it effectively splits between the two voltages, right? And so when you look at the equivalent resistance here, where do you go from here? Yep. So you can say that effectively this one, because these are equal, you can just say, okay, this is R1 on 2, this one is R1 on 2. And so you can say, therefore, RL equals. So now we can apply our quad 1 method of just calculate the impedance. We just short the source, right? And then that means the two resistances are in series. So you end up with R1 on 2 times 2 equals R1. So therefore, R1 equals 50 ohms. So a very long way of getting to it, but like this is quite a tricky question, right? The trick is in developing, you kind of have to develop an equivalent circuit model. But when you're considering any sort of load resistance, you need some sort of circuit model. So that should be your first goal in calculating these impedances. Usually use the Thevenin impedances when, in the case where you're trying to model one circuit and you're trying to just squeeze it down into one resistance and then fit it into a circuit like this. But in that case, we don't really need to apply that method. So, very quickly on the last question. So actually, my iPad is about to die. It's on 1%. So that is very unfortunate. So I'm going to let my iPad charge for like 2 minutes and then quickly go through the question. Feel free to stay. I'm just going to quickly disconnect this. Charge my iPad for like 2 seconds. Okay. But effectively, the question was about, so a failure mode and effects analysis is now carried out on the circuit in which simple short circuit and open circuit component failures are assumed. So what do we know about failure effect analysis? Nothing? Yes. So when we're doing failure effect analysis, we're assuming worst case conditions. So you're assuming when a component either shorts or when a component opens. So you kind of have to backtrack and say, what was the function of the circuit initially? When I short this particular node or when I open this particular node, what happens to the circuit? Okay. So I will go to the last question because it is quite tricky in about 2 minutes. Sorry it is going over time, but if you need to leave, please feel free. It will be recorded. Okay. Yep. Yep.
Yeah, maybe can you just fill out this attendance form?
Yeah. That's not that hard to charge. It's on. So slow. There's no way to like dual charge and this doesn't charge, does it? Oh, but now I feel like it's charge.
Hey guys, before you leave, can you just scan the QR code and sign up?
What's it on the stream? On the live stream?
Oh, it just shows the rainbow colors.
Okay.
I mean, instead of like talking about, I could put the video right back to you.
No, that's okay. See you guys. All good. See you guys. Good. Good. See you guys. Okay, one more minute and then we'll go through it. Sorry for the wait. See you guys. That 2%, like try going through it in 2%. Yeah, I'll run through it now quickly. Find where it is. Okay. So for the purposes of time, I'll just go through the open circuit. The short circuit is almost like a very similar argument. Okay. So let's go through. Yep. Do that. So it's on 3% on. Let's go. Okay. So is it not up? Okay, we're back. Okay, so find the effects of R1 failing. So that means if I look at my circuit here, so if R1 fails, that means it either opens or shorts. So let's just consider the case where it's open. Okay, so if it's open, so I'll just copy this circuit, take it down here to E. Like that. So just delete this. So if R1 opens, that means it's gone. It's now open. That's still node X. So if Vx is open, what is the voltage at Vx now? What is that offset voltage? Ground. It's just purely ground, right? We don't have a voltage division anymore. It's now grounded. So implication number one, Vx is grounded. Right? Now, what is the implication on Vx not being grounded? Oh, sorry, on Vx being grounded. Yes, so it's going to do funky stuff. So that's one of them. So I'll call that number 3. We'll get to that after. What's an implication in terms of the value of RL we calculated before? Yeah, so now there's going to be a mismatch in impedance because we no longer have a 50 ohm transmission line. So, and again, for a question like this, you don't really need to calculate the value unless it supplements your answer. But here, all that matters is that the effect is that there's going to be reflections. The specific amount of reflections doesn't matter. Okay, so mismatched impedance. Is the audio still okay? Yep. Mismatched impedance, therefore will be reflections. Okay. Cool. And then the third thing, so these are good, but the third and most important point is what effect does it have on the circuit's operation? That is fundamentally the most important part of failure analysis. So we spoke about what the point of the circuit was here, right? We said if A equals 1, then the output here should be 1. So what we need to do now is consider, is that still going to be the case with R1 open? Okay, so let's analyze. So let's see what happens. So with A equals 1, that means current is going to go this way into the node, and it's going to leave the node in this case, just based off of this sort of diagram we've drawn here. So for Vx, it's going to be driven into the node. For Vy, it's going to be driven out in the other direction. So in this case, so we can draw what the direction is going to be for A equals 1. So for A equals 1, the direction here is going to be into the node. So Ix, and then we can just ignore RL. And then we also have the same thing for this one, where current is being driven. No, that's okay. Yeah, it's okay. I've got enough. So okay, so then current in this node will be leaving, just based on the A equals 1 scenario. Is that okay so far? Cool. And then, so let's calculate what the voltages will be. So at Vx, the DC offset will just be 0 because we're grounding it. What would the current be? What would the voltage be due to the injection of current? Yeah, so just be R4 times Ix, so equals I4 times Rx, which is, Rx should be R1. I don't know why I wrote Rx. Or R4. R4 equals 0.5 volts. Okay, then we need to calculate what Vz is. Now Vz is basically the same thing we had before. It still has that voltage offset of VCC on 2. So if I recall back the normal formula we had, so it still has that voltage offset. And we've set R3 equals to R1. So VCC on 2, and will it be plus or minus current? Minus, right? Because at this node, it's leaving. So minus 10 milliamps multiplied by what resistance? Not 50 in this case, because remember, on this node, effectively what we have is we have a resistor up to VCC and then to ground. That's effectively what we have here. Yes. Yeah, so it'll be 25. The same argument we had before. So it'll be just R1 on 2, because all of the resistances are the same. So it'll just be the resistance divided by 2 because it flows through that parallel combination. And so then this will be 1.4 volts. Is there any questions on these steps here? Anything that's confusing? So effectively, I've just considered the failure mode we have, what happens for A equals 1. And so what we find is that Vx is less than Vz. Is this a problem? Why might this be a problem if I look at this part of my circuit? What was the intended operation when A equals 1? Yeah, so the intended operation was that Vx is that we have an output here of 1 as well. The only way we can achieve an output of 1 here is if Vx is greater than Vz because it's a comparator. Right? So in order to go from having a 1 here and transporting a 1 here as well, we need this relationship. But what did we just derive? Happens in the failure mode. The opposite, right? So what actually happens is we get an output of 0. So in other words, incorrect operation. Okay. Now the investigating the short is exactly the same. You just analyze what happens to those voltage nodes and then you go from there. Failure analysis is always the same. You're just analyzing what is the implication on the operation of the circuit as a whole. Okay, so just do it fairly methodically. With that, thank you for staying for the extra time, but that is the last question for the paper. Thank you very much for attending. I really appreciate it. Again, I really appreciate those of you who stayed after. I hope it was helpful. And yeah, if you have any questions, I'll be staying for a bit after as well to answer any of those. But yeah, best of luck with your studies. Good luck. Thank you. Thank you. Yeah, thank you guys. Really appreciate it.